So dear participants, on behalf of the Royal Academy, or Swedish Academy of Sciences, as a member of the class of physics and former vice president of the Academy, I wish you all very welcome to this timely and exciting symposium on gravitational wave science here in our beautiful Bayer Hall. The Academy has a long history since 1739, when the famous botanist Carl Linnaeus was one of the founders of the Academy. The prime objective still today of the Academy is to support and foster good evidence-based science and bring it to the general public. One important way to do this, and what the Academy probably is most well known for internationally, is to award Nobel Prizes in physics and chemistry, which it has done since 1901. And as you know, in 2017, the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics to Rainer Weiss, Barry Barish, and Kip Thorne for decisive contributions to the LIGO detector and the observation of gravitational waves. This great discovery started an exciting new era of gravitational wave, astrophysics, and cosmology. And in this symposium, our lecturers will present the current status and outlook of this novel window to the universe. And we are grateful to one of the 2017 Nobel laureates, Kip Thorne, for sharing his thoughts with us through video link after the reception today at about 6:15 in the afternoon. So I will now give the word to one of the coordinators of this meeting, Ariel Goobar, for some introductory remarks about this symposium. Thank you, and please.
Thank you, Lars. Thank you very much. I guess I'm less prepared than you are. Well, thank you very much to the Academy for generously supporting us in this, organizing this meeting. Thank you very much to the speakers here with us today. We have quite a lineup, so thank you very, very much for joining us and telling us about exciting science that we have. And thank you to the audience for being here to share this symposium with us. As Lars was saying, I think if not clear now, it should be clear after the talk today that the discovery of gravitational waves is arguably among the most spectacular discoveries in science for many reasons. Starting from the technical reason, from my mind, is mind-boggling that the emission of gravitational waves from sources at cosmological distances can be detected at Earth with tiny perturbations of an instrument of strains of order 1 part in 10 to the 20. It's quite remarkable. It's equally impressive for fundamental physics and cosmology that we can study the interaction among black holes, arguably the most exciting and extreme objects in the universe. And as we also will be hearing more today, it's combined with electromagnetic information, we can gain very impressive information about how neutron stars work, where the heavy elements are synthesized, and also, as you were saying, as I think will come up, they measure the Hubble constant. So for all these reasons, we are super excited about hearing from you today. And from our point of view, from the organizing committee, what we are aspiring that this very exciting window to the universe that people will be, the discoverers will be telling us about, is made very well known to the Swedish community. We are really hoping that the Swedish community physicists and astronomers alike, will take this on board, and we hope to see a fruitful development of gravitational wave science in Sweden. So that's hopefully this works as an embryo for that. And yes, the last thing I was going to say was, for just Lars to say that it was maybe not obvious to everyone looking at the program online, but we are very fortunate to have Kip Thorne talking to us at the very end of the meeting. So please stay until the very end. Without further ado, then I give the word back to Klaus to invite the first speaker. Okay.
Okay, so the first speaker is Patrick Brady from University of Wisconsin-Milwaukee, and he's also a spokesperson for the LIGO scientific collaboration. And the title of the talk is Gravitational Wave Astronomy, Progress and Perspectives.
Thank you. It's a great pleasure to be here. on a beautiful day in Sweden. I hear the weather's always like this, so I'll be back. I also want to thank everyone for organizing this meeting and for the invitation to speak to you. So I'm going to give you a pretty broad overview of gravitational waves, where things stand in gravitational wave astronomy. So I want to start by just thinking a little bit about the gravitational wave spectrum, akin to what we think about when we talk about electromagnetic astronomy. Represented on this graphic from the left is the very lowest frequencies of gravitational waves, stretch at around 10 to the minus 16 hertz or so, stretching up to the highest frequencies of what we think about as gravitational waves at the moment, although there could be sources at higher frequencies, around 1 kilohertz. And if you look above the colored chart, you see the types of sources that we think may exist in the universe to generate gravitational waves at those frequencies. And then if you look below the chart, you see information about what we think the current types of detectors today or in the near future that could give us access to the waves in those frequency bands. So just to get us started, let me begin. Try this. Okay, there we go. It's a little weird. Okay, so let me start with the highest frequencies here. So LIGO, Virgo, Kagra, that's the set of detectors that operate today in the audio band around 100 hertz or so. And I'm going to speak mostly to that during my talk. But I also want to draw attention to the other wavelengths and the other detectors, and I'll say a little tiny bit about them at the end of my talk, but then that'll lead into the other presentations through the day. So when we get down below 1 hertz, down roughly around 10 to the minus 3 and 10 to the minus 4 hertz, we have space-based detectors, which we anticipate could fly sometime in the next decade to be able to detect gravitational waves. We move on down, and we heard over the past year about pulsar timing arrays, which are a novel way to detect gravitational waves in the nanohertz frequency band. And so that one is also something that is now being realized as a detection method for gravitational waves. And if we look down at the very lowest frequencies down here, if we use the cosmic microwave background, we're able to access the very lowest frequencies of gravitational waves on this graphic. Now the sources themselves, it's most abundant, as you can see, up in the high end, where we have the compact object mergers, perhaps supernova explosions, and also spinning isolated neutron stars, as well as some sort of background of gravitational waves coming from throughout the universe, similar to the cosmic microwave background, except in gravitational waves. As we move down in the frequency band, we want to go to higher masses. I'll explain a little bit why in a few moments. But for this LISA band, galactic binaries, in particular white dwarfs in binary systems, actually are clearly a dominant source of gravitational waves for that frequency band and for that detector. But we also begin to access supermassive black holes and not just stellar mass compact objects. And then when we go down to the lower frequencies, still it tends not to be the individual gravitational wave signals that we access, but the background of everything humming throughout the universe. So as I said, I'm going to focus on LIGO, Virgo, Kagra. Keep on. And so the first thing that I want to introduce today is the International Gravitational Wave Observatory Network, which is made up of detectors in North America. We have a detector in the northwest, LIGO Hanford, detector in the southeast, LIGO Livingston. There is the Virgo detector in Italy. GEO is now an exploratory detector in terms of technology exploration. Kagra is a Japanese detector, and LIGO India is under construction. The pictures across the bottom gives you a sense of what these things look like. On the bottom left is the LIGO Hanford Observatory in the desert in the northwest of the United States. And then we have LIGO Livingston, we have Virgo, and then we have the underground detector at Kagra. The basic principles of operation of these ground-based gravitational wave detectors is laser interferometry. So in its simplest form, this cartoon captures enough about it for us, especially at this point in the discussion. The basic idea is that there is a laser source that is sent onto a beam splitter here in the middle. It then sends waves down to arms. Typically, they're made perpendicular, don't have to be, of course. There is a test mass that's suspended at the end of each arm, the laser light is reflected back, and if the arm lengths are unchanged, so they sit there and they're not changing much, then we tune things up so that there's no light actually returned back onto a photodetector down here. When a gravitational wave passes, it causes one of the arms to stretch, say this one here, so it stretches out in this direction, and simultaneously the other arm is compressed a little bit, and so you get a shift in the interference pattern, and so you get a signal having light and photons arriving at the photodiode down here at the bottom. So a gravitational wave causes the arms to stretch and shrink in this type of configuration as they go by, and thereby we measure the gravitational waves as a signal on the photodiode. Now, these detectors are highly complex. They're servo-controlled at almost every level, but they act as if the test masses at the ends, which are mirrors to the laser frequencies, they act as if they're in free fall, and as a result, we can check out what the different primary noise sources are within the gravitational wave detector. And this representation here of the strain spectrum for the strain noise spectrum for such a detector, this is Hanford and Livingston. This is in the early parts. This is actually observing run 1, which I'll explain in a moment. And you see this characteristic bucket shape with a minimum living around 100 hertz, rising at the higher ends in the kilohertz regime, and then rising again at the low frequencies down to around 10 hertz. In the high frequency end, that's dominated by laser noise and in particular photon counting statistics associated with these detectors. So this is all about how much power we can get inside of these detectors and how many photons we have arriving at the photodiode. Down at this end, it's dominated by vibrational noise on the surface of the Earth, and so this is all about us somehow isolating from the vibrations of the Earth's surface. And then down in the middle, the dominant noise source used to be just internal thermal noise associated with these detectors, and certainly it's a key piece of the noise in there now, but now we're also beginning to access other fundamental noise sources such as radiation pressure and quantum noise in the detectors. So this here is the picture you should carry when you think about a ground-based gravitational wave detector, whether it be the ones in operations today or the ones that will be in operations towards the end of the next decade. In terms of gravitational wave sources, well, everyone by now knows, and most of the rest of my talk in terms of sources is going to focus in on the detection of gravitational waves from pairs of compact objects, black holes or neutron stars, stellar mass, that go around each other and crash into each other as a result of emitting gravitational waves and causing their orbit to shrink. So in this picture on the right-hand side, I'm demonstrating two objects, meant to be black holes in this case, orbiting around each other in close to a circular orbit. They generate gravitational waves, which are oscillating down here at the bottom, and this is what we call the strain. It is the amount by which the detectors are shifted in the motion like this as they pass. As the gravitational waves are emitted, they carry energy away from the system, and therefore the binary tightens. And so what you get is this characteristic shape where as the two objects come closer and closer together, eventually merging and turning into a single black hole in this case, you get this shift in the frequency upwards until the merger where it suddenly shuts off, and then the final black hole rings for a little while and rings down to a stationary Kerr state. If you want to think about the strength of gravitational waves, a good way to do it is given by taking a look at the quadrupole formula, which was first written down by Einstein, and then taking a look at a binary system like this in, say, a Newtonian orbit or other things. But when you go through the math, roughly speaking, the scaling for the strength of the gravitational waves is shown here in this equation. And I want to draw attention to a couple of pieces in it. First of all, this mass here, This mass is the amount of mass that's in the time-changing quadrupole moment of the system. And so that's one way that you can estimate how much mass is involved and what is in the numerator of the gravitational waves. The second term that's important is this v squared term. And so what you want to do is you want to get a lot of time-changing quadrupole moment, and you want to get it moving very, very quickly in order to have the strongest gravitational waves. And then finally, you've got the 1 over r term, which tells you that the wave strength will fall off as 1 over the distance to the source. So this is the reason why compact objects are actually one of these very wonderful recipes of nature for gravitational waves in the ground-based frequency band. First of all, we know we have black holes and neutron stars. If we go with stellar mass, these are things that are kilometer scale or 10-kilometer scale in terms of their size. And so as a result, when you put the two things in orbit, they can get within 10 kilometers of each other as they're orbiting around. So you can get very, very high frequencies, very fast orbital motion, and by putting black holes in the system, you can get very high masses. So these are ideal systems that are created by nature for generating gravitational waves. So let me now go to sort of, that was the preamble to where we are. And so what I want to do now is tell you a bit about the observing runs that we've had so far. So back in 2015, whoops, I keep on doing that. Back in 2015, we started what we call Observing Run 1. Okay. And LIGO were the only two detectors that were participating in the run. As you go across here, you see the colored bands indicating the different runs that we've gone through, 01 through 04 so far. And you see then also when Virgo and Kagra also participated in the runs as the colored bands going across. I want to draw attention to the number that appears above each run. This is a measure of our sensitivity. This measure is what we call the binary neutron star merger range. It is the distance to which we're sensitive to gravitational waves from a pair of colliding neutron stars that are optimally oriented relative to the detector. That means that they're located directly above the zenith of the detector, and the orbital angular momentum is pointing directly towards or away from the detector. So this gives you a measure of the sensitivity as the noise in the detector, as you saw as a function of frequency before it gets lower and lower, then this range increases. And this is just our standard of measurement to kind of state in a simple astrophysical way how sensitive the detectors are. If you take this number and you calculate the area of a sphere with that radius, that tells you, and multiplied by our observing time, that tells you the space-time volume that we've actually accessed during the observing run. So 4 over 3 pi times 80 cubed multiplied by 3 months for observing run 1 is the amount of space-time volume that we actually access. So it's a very useful number in terms of thinking about rates as well as thinking about sensitivity. So if we take a look here, and I'm going to say a little more about it now, we notice that 2015, almost 10 years ago now, 150914, this is our naming convention for gravitational wave signals that we detect. We detected the first merger of a pair of black holes, and that's the one for which the Nobel Prize was awarded in 2017. And then you can see the evolution through the runs. In the second run, we were pushing up to 100 megaparsecs in sensitivity. Virgo joined near the end of it with about 30 megaparsec sensitivity. And everyone's aware of what I'll talk about a little more now, 170817, the first binary neutron star merger that we detected. Pushing into 03, we got up to about 110 was really the average, but around between 100 and 140 megaparsecs in range. Virgo and Kagra also participated, and this also marked a significant change in how we approached the field because we were able to announce our detections immediately upon making them within minutes of the gravitational wave signal passing the Earth. And today we're in observing run 4. Over here, you can see that the sensitivity is now increased up to between 150 and 170 actually now megaparsecs, where we have two parts to the run. We designate them O4A and O4B. Virgo was not able to join the start of the run, but is participating in the second part at the moment. And Kagra, similarly, is continuing to commission to try and actually improve its sensitivity. All right. So this is the story of the runs that we've made with the gravitational wave detectors. I want to highlight one piece of this, and this is, you notice, we turn on and turn off, turn on and turn off. This is because these things are incredibly delicate instruments. We're not in a position whereby we can just turn them on at the ultimate sensitivity and let them run and stay there. So we have to do multiple things. We have to do a significant amount of maintenance to the systems, even when we're holding fixed at a given installation point. And then as we stabilize their operations within an observing run, we plan out the next steps in our sensitivity improvements, which take years usually for anything significant. The one thing to note on this here is there is a gap, of course, from 2020 up until 2023. About 2 years of that was actually taken up by the pandemic, which really did sort of set the field back in terms of the instrumental progress. So, in terms of detections, we've already talked about most of this, but I thought I'd highlight it for everyone going through the sequence. So on this graph on the right, what you see is the primary mass in the binary system. So along the horizontal axis, that's the primary mass going from 1 solar mass up to 100. Vertical axis is 1 up to 100 for the secondary mass. We plot everything where the primary is taken to be the larger mass in the system. So each of these little circles with 2 dots on it represents a binary merger that we detected in gravitational waves. And 150914 up here around 3030 in solar masses is the first detection of gravitational waves. And we shouldn't underestimate its impact. First of all, in demonstrating we could actually measure waves, very significant. Second, in terms of actually observing for the first time something that was directly attributable to 2 black holes. And so really, really gave us that first look at these 2 black holes in isolation. And then finally is the sort of surprise that we've often lost sight of now as the number of detections has gone up, that we were seeing black holes of this mass. The anticipation initially had been 10 solar mass-ish would be where we would see the first detections of binaries. And so this higher mass was a bit of a surprise at the time. The second detection I've already mentioned, the second significant one I want to mention is 170817. This was the first binary neutron star merger. It established right away a very important result because there was a gamma ray burst that was observed almost simultaneous with it, just 1.7 seconds apart. And this established that binary neutron star mergers are the origin of some of the gamma ray, short gamma ray bursts that we see. 190521, another object that came with its own sort of unusualness. It's up in this high mass regime, up around 100, almost 100 in primary and around 80 solar masses in secondary. And so this is up into this high mass end where questions about stellar evolution and whether or not the black holes in this system can form by direct stellar evolution or in some other way, like actually hierarchically merging several black holes already, start to arise. And this is up in a regime where people expect that there should be pair instability taking place inside of the very old stars, and potentially then you get a pair instability supernova. And it was thought that actually below this mass that the pair instability should kick in. And when you get a strong pair instability supernova, you actually disrupt the star completely and get no black hole remaining. So there was expected to be this cutoff at the higher masses. And so far, we're still learning a lot about that high mass regime and the pair instability. Finally, on this graphic is 190814. This object, you can see, has a primary mass somewhere around 25 or so to 30 solar masses, and a secondary down around 3 or 4 solar masses. This object is a bit unusual because we don't know if that secondary is a neutron star, so low mass around 1.4 solar masses and actually has a surface, or if the secondary object is a black hole. So that one has left us with a little bit of a mystery, and we'll come back to that mystery again in a couple of moments. So taking a look then a little closer at the mergers that involve neutron stars, 170817 I've already told you about, but there's been a second neutron star candidate, which is 190425. So for those less familiar with these phone numbers, 19 is the year, 2019, 04 is the month, and 25 is the day. So this was detected in the third observing run. So we've got 2 candidate gravitational wave signals from pairs of binary neutron stars that merged. To think how important these mergers of neutron stars are, 170817, which is beginning to look more and more like an extremely lucky event for us, which we already really knew because it was fairly close by, gave us some absolutely wonderful things. One of my favorites to call out is how accurately we were able to limit the difference between the propagation speed of gravitational waves, which by Einstein's theory is the speed of light, and the speed of light, by just using the gravitational waves and the time delay between the merger and the gamma ray burst that was observed 1.7 seconds later. Just using those 2 pieces of information, you can measure very approximately the distance to the binary merger using the gravitational wave signal, using the time delay, and then you get this constraint on the speed difference in the speeds. And it comes down to 1 part in 10 to the 15. So this amazing constraint on the difference in those speeds from that single observation. And kind of wonderful because in terms of the excitement around this event, this was something that many people within the collaboration identified within 24 hours. So the day before, the constraint was 10 to the minus 4 or something like this, and 10 to the minus 15 the day after. And it was just a lovely result. 170817 was also, there was also an optical counterpart identified to that source, AT2017 GFO. That optical counterpart demonstrates all the properties of a kilonova explosion, which is the type of optically powered explosion where you expect afterwards, after the merger of 2 neutron stars. And so that association has brought just a wealth of information about the structure of neutron stars, what we can expect for the future when we see such collisions, the origin of the heaviest elements in the universe. So a particularly exciting result. On the right-hand side, I show another one of these plots, which is the mass on the horizontal axis, from around 3 solar masses down here up to around 25, and on the vertical axis it's from 0.9 solar masses up to about 2.75 solar masses. Each one of these contours represents a 90% confidence interval on the pairs of masses in a particular binary system. The binary systems are labeled down the right. So 200105, 200115, 190814, and 190426. And what I want to particularly draw attention to is 200115, which was a very confidently detected gravitational wave binary merger. And you can see that the contour for the pair of masses lies solidly in a regime where it's between 5 and 10 solar masses at its peak, and it's down below in this region around 1.3, 1.4 solar masses for the secondary. So with these 2 masses, the higher mass that makes us think that this is a black hole, and this mass being around 1.4, strong confidence that this is actually a neutron star. So this was really the first confidently detected neutron star black hole binary. Again, one of the interesting things to think about this particular event is that through the years of observing neutron star binaries within our galaxy, one of the things that has been chased in terms of pulsars was, first of all, isolated pulsars, second of all, pulsars in some sort of binary, finally, binary pulsars. But pulsars orbiting a black hole were long sought, never observed, and then seeing this is the first time we actually get to see such a pair of objects, which you guess have to exist, but there are all kinds of stellar evolution scenarios which could cause the rates to be very, very low. So it was really gratifying to see these events. So if we take a look at the detection rate, this tells us again about where we are in the field as something that started so recently, less than a decade ago, in terms of having real observational results. We started out in the first run with a few detections down here. Second run, we added and we came up to around 12 by the end of the run. And then you can see this change in slope, where the detector sensitivity increased significantly from 02 to 03, and so the rate of detections increased significantly. Along the horizontal axis is the number of days of observing data that we took. And 04, it's actually a little harder to see the change in slope here, and there's actually probably a secondary effect going on. This is the detections made in low latency, and so whereas the 03 events are actually the full detection catalog, including a deep offline search. So it's likely that by the time we fill things in on this axis, you'll be able to see another change in the slope more significantly up here. But still, what you get to tell here is we went from having a few detections a decade ago, and we're up past 150 now. So we're beginning to get into the regime where we have a real catalog and a real sample of objects in which to ask questions. Which brings me to one of the major pieces of work that we've been doing as we increase the number of detections is to try to understand the nature of the rate of compact binary mergers as a function of the masses of the objects and the spins of the objects within that sample. So this graphic comes from one of the LIGO Virgo Calgra papers, and it's just an example. There is a wealth of LIGO Virgo Calgra work and then a whole wealth of other work following on from this, some of which you'll hear about through the course of today. What you note when you take a look at this is each of these curves is an effort to map out the spectrum, being the rate of mergers as a function of the primary mass along the horizontal axis, going from just down here around 5 solar masses up to 100. Each of the curves has a certain assumption, either about the method used to make the calculation or the prior probabilities associated with the formation of the binaries of stellar evolution. And when you take a look at it, you still can see by eye this tendency to have rise up to a peak somewhere around 10 solar masses, a fall off down towards 100 that, if you're an astronomer, you'll call it a power law. But you also to draw your eyes maybe to this bump here, and you start to say, well, this is great, we've got a bump. Now let's find out what's causing it. So this has been an area where a lot of focus of trying to understand stellar evolution, binary formation, and so on has looked to try and explain whether or not that feature is actually something that will persist and can be understood. And as we get more detections, we'll actually be able to resolve this much better. So this is one of the key things that we're learning about as we go through. And I'll mention just for that bump that the possibility there is, there's all sorts of stories around what it might be because we really don't understand stellar evolution very well. So there are possibilities that it could be a second population of objects where the primary set of objects in this are okay. Sorry, I was looking at the wrong time too. The primary set of objects in this are from the field, and then this is actually from another formation mechanism. So with the fourth observing run ongoing, it started on the 24th of May 2023. It's been ongoing up to now, split in two parts with a commissioning break in the middle to take care of things. The most important thing I want to draw attention to on this particular slide is this. 03, we were detecting one binary every 5 days. In 04, we're detecting them one every 3 days. That rate of detections is climbing, and by the end of the decade, we expect to see quite a few more. So I'm going to highlight one more result that is very recent. This is the first result coming out of 04. So we have a representation here, which on the vertical axis shows solar masses. Each dot on this represents a compact object. The horizontal axis is nothing except spreading things out so we can visualize them, and the particular location and shape has no importance. But what you can see here is several different types of object. There are black holes that were observed in the galaxy using X-ray observations, for example. There are pulsar measurements of neutron star masses. And then there are gravitational wave observations of pairs of black holes that collide to form a third black hole, and pairs of neutron stars that collide to form a black hole. And so what we have on this diagram, for every detection that we make, we add 3 more mass measurements to our knowledge of black holes. But in particular, if you take a look then at the electromagnetic pieces, you'll notice that there's sort of this dearth of detections with masses inside of this region between 3 and 5 solar masses, which has been referred to as a mass gap. And one of the questions that remains open is whether or not this is an artifact of the observational methodologies or some other selection effect within the observations in the galaxy, or if it is truly a feature of stellar evolution. And just earlier this year, we announced the detection, one of our first results from 04, which actually measures a binary system in which we confidently can say that one of the masses is in that 3 to 5 solar masses range. So in this diagram, you again get to see across the horizontal axis. Get that right again. Across the horizontal, you get to see masses from 1 up to 6. This was 1904-25. That was a binary neutron star. 200115, we think, is a neutron star black hole. 1908-14, the secondary object was down here just below, but we don't know if it's a neutron star or a black hole. And if we move on then to what we were able to see recently from 230529, the primary has a mass up here, right here in the middle of this mass gap region. And so the question is, what sort of object is it? Is it a really, really high mass neutron star of some kind? Is it a black hole? We actually are not able to tell from the gravitational wave detector data alone. Skip that in the interest of time. So the next point that I want to emphasize is one that's important to electromagnetic astronomers, which is the rate of binary neutron star mergers. We've got 2 candidates so far. 170817 was extremely close by, and we have now been able to take 6 months of data with 04. And so what we now know is that if we went into, as we went into 04, we were able to use the 01, 02, and 03 rates and say that we expected 0.4 to 7 new events during 04A. We got none. And so it's very easy to estimate what we think the rate is for 04B, and it's going to be 0.2 to 3.5, roughly halved. That corresponds to about 5 per gigaparsec cube per year, up to around 800 per gigaparsec cube per year is the rate now that we've taken data during 04. So it halved the rate that's published at the present time. So this shouldn't be surprising, but we were all extremely optimistic after 170817, but it is telling us that this that multi-messenger astronomy, so being able to observe both gravitational waves and electromagnetic signals, is going to be really, really tough. I'm going to pause for a moment because about a minute ago I got a 10-minute warning from the top, having had a 5-minute warning from the bottom. So, but yeah, I'm going to take the later.
5 more minutes.
So there are many more observational results. I'm not going to put any time into these today, but I wanted to just put up the graphs. On the top left, you see searches for continuous waves, and these are upper limits on such searches. The bottom left, you see searches for a stochastic background of gravitational waves, and again, there's only upper limits so far. And then on the right, you see the Hubble constant measurements we've been able to make. Primarily, the most of it of its power comes from 170817, but you can also do some additional things with the Hubble measurements using the population of binary black holes, and it informs a little bit. But all of this is other science that's going on. You'll hear more about some parts of it as the day unfolds. So let me I'll skip over that for a moment, and I just want to tell you about the 5th observing run. So the 5th observing run is coming in 2027. This graphic is probably going to end up sliding a little bit. The 04 will go through the early part of 2025, and the 05 run will start around the end of the second quarter of 2027. We expect 05 to continue then for several years. It will not just be a one-year run, it'll be a multi-year run. The sensitivity should take us from this 160 or so megaparsecs at the present time with LIGO up to somewhere in the range starting from 240 up to 300 megaparsecs in 05. So you can see that this nearly doubles the range. That nearly multiplies by a factor of 8 in the rate of detections of compact binaries, and in particular for neutron stars, that's promising for us. So this really explains why we need to keep pushing this sensitivity. Without those pushes, you simply cannot increase the rate, and especially for these unusual objects. Now, looking to the early 2030s, I mentioned at the very beginning that that there's an observatory under construction in India. We expect that the LIGO Observatory will begin operating in the early 2030s, so that will be built exactly in the same structure and design as the LIGO instruments. We're also targeting an upgrade to the current detectors, which is the upgrade is designated as A sharp, which should get us another factor of 2 on the sensitivity over the 05 range there. So we're talking about going up by a factor of 64 in rate from where we are today. So you'll be detecting binaries many times per day by the time we get into the early 2030s. Virgo is also speccing out a similar upgrade, so we're hoping that we'll have a network of detectors that are all at that similar sensitivity in the early 2030s. To give you a sense of the type of science we can do with that, you begin to really open up the numbers of objects we can detect. We begin to be able to make more accurate Hubble constant measurements. We'll be able to understand the statistics of the binary mergers and perhaps tease out the different types of formation channels for those binaries. We'll be able to do some black hole spectroscopy, looking for subdominant modes, and hopefully, if we have enough neutron stars and they've got high enough signal-to-noise ratios, we'll be able to measure the radius of the neutron star below a kilometer. I'm going to quickly go over, just go back again to that spectrum from the beginning of my talk. I'm going to quickly go over some other things you're going to hear about in much more detail as the day goes on. So the first item is the recent pulsar timing results from earlier, from 2023. The graph I show is known as a Hellings-Downs curve, and Chiara will hopefully say more about such things in her talk. And at its core, the results that have been seen from these pulsar timing measurements now give evidence for a gravitational wave background in the nanohertz frequencies with 3 to 4 sigma, depending on exactly which statistical analysis is given. So it's very, very compelling that we're actually getting there. The next thing that I want to highlight is the LISA mission. So the great news about LISA is that it is now slated for a launch sometime in 2035, and this is fantastic news. I now know it's going to happen because it's closer than 12 years away, and it's always been 12 years away when I was a graduate student. So it will happen, and it is going to be a fantastic mission. The number of gravitational wave sources that are accessible using this instrument is just off the charts. Clearly, it's dominated by the white dwarf background, in fact, causing most of the noise at the lowest frequencies. But then we get at supermassive black holes. We might get at extreme mass ratio black hole or binaries where we have neutron stars going into supermassive black holes. All sorts of interesting science that we can get with this. And I'm going to finish now with just a little bit of a highlight of next generation detectors. So I told you where we started in 2015, brought you through to our observations and our current observing run, and pointed out at least where the current generation of detectors are headed in the start of the 2030s. And all of that is fantastic. We're realizing the science that we had hoped to be able to do, and we constantly, with every improvement in sensitivity, may access new sources. However, the work to design next generation facilities is now well underway. There are two projects that are moving. They're at various statuses of existence, but I'll call them projects for now anyway. The one at the top left is Cosmic Explorer, and this is a design that's being championed out of North America and is intended to give a sensitivity 10 times more in amplitude to gravitational waves than the current generation of detectors in 05. And the way they're going to do that is essentially they're going to go from the current generation of detectors, the arm length is 4 kilometers, and they're going to bump it up to 40 kilometers. So just multiply it by 10. Simple. No, not so easy, but still, that's what they're going to do. This is absolutely great. The other concept and the other project that's well underway is the one in Europe, which is the Einstein telescope. This is intended to be current design is a triangular configuration involving multiple detectors within the first system, 10-kilometer arms underground, possibly going cryogenic at certain points. So pushing the limits in a totally different way in terms of trying to achieve the sensitivity. But nevertheless, between these two detector designs and having them in place, you start to be able to access a whole new set of science. You can really detect all of the black hole mergers throughout the universe. You can understand then the evolution of the cosmic evolution of the merger rate of binaries as you look through it. You can understand the dynamics of dense matter much better through higher signal-to-noise ratios and greater rates. And hopefully, of course, you can detect things that we haven't found yet, like spinning neutron stars that happen to have distortions and generate gravitational waves, or cosmic string cracking somewhere out in the universe, or some other particularly unthought of thing. So with that, I'm going to end, and thank you.
Thank you very much for this very nice overview. It's time for questions.
Well, I can start then. So thank you very much, Patrick. So you emphasize a lot about the masses of the compact objects, and when we look at those graphs, I mean, should we assume that there are no selection effects? That what you see is actually the real, is what there is out there?
No, there are selection effects for sure. And let me see if I can go back to one of the graphs to just give a sense. There are selection effects for sure. So when we look at let's look at the scatter plot here, right? This is the one where you kind of worry about it. So there definitely are selection effects. So the first thing is that the gravitational wave mergers occur at frequencies that go at 1 over the mass of the system. And so the trouble is that the highest frequency of gravitational waves observable from a binary system, they go downwards as the mass goes up, and they creep out of the band at the lower end. So at the upper end here, clearly we're going to actually have selection effects cutting off in principle the masses that we have. That should be the primary one in this regime. I mean, we also have other selection effects associated with the more extreme mass ratios, where we actually are less we're less capable of making detections in some of those extreme mass ratio regimes, and so there can be selection effects over there in that region. But within the region that sort of sits in a band close to, within a region that sits in a band close to the equal mass line and up around here, we should actually be in pretty good shape. A couple of other things that I will mention is we do not search, we actually have no eccentricity in the binaries in our searches. And so that could have an impact if there are a lot of systems somewhere that actually form with significant eccentricity. The idea here is these formed long enough ago that the gravitational waves actually took away the eccentricity, and so it's not actually important. So that's a few. I don't think there are other major ones. When we look at the next graph with the rates, this one actually tries to take out all of those selection effects.
Okay.
Question about the mass gap event. There still seems a lot of open questions about it. There's a big error band on it. We're not sure if it's a black hole or neutron star. Is there any hope for further analysis of the event, or is it just that we have to hope for another one to come?
Yeah, great question. You know, what we've done so far with it is the best we have been able to do so far. It really does try to look for effects from the possibility that there are tidal distortions of a neutron star or some other solid object. We haven't seen any evidence of that. I think, now I'm going to speak personally, I think it's unlikely that we're going to tease out more. There will be analyses that try to take more prior information and try to do work on it. There absolutely will, and there should be. But I think it's doubtful that we will actually tease out more information about what that object is from that current observation. So we're really reliant on getting more of them. And you know, what will really be good is if we can get the rate up high enough. If we ever find an NSBH where we do have an electromagnetic counterpart, and then start to be able to do that question about both. Because if we saw an electromagnetic signal, then we'd probably go, you know what, there's got to be some matter outside the system that led to the electromagnetic signal. So this is going to be the direction we want to go. The nice news is that the rate of these higher mass ratio events is going up, and that's great. Unfortunately, the distances are also going up, and so whether or not we're going to be able to find electromagnetic counterparts is going to be something we're going to have to wait and see.
Okay, thanks.
Yes, sir.
So you mentioned that O4b may be slipping. So how is the discussion going there, and when will we know?
Yeah, so that discussion started about about a month ago. So it isn't so much that it's slipping. There's a combination of things going on. So first thing is that there's actually been some great progress in terms of coatings on the mirrors, which are one of the major limitations for the O5 and post-O5 upgrades. And they're trying to get those new coatings scaled up onto the large test masses. And that's taking a little more time to work with the vendors to get it done. So that's one of the things that's sort of feeding this. On the other end, Virgo has some extreme challenges. It's turned out that they have a design in their system that they really have to correct, and it's going to cause them at least a year of extra time in the gap between the two runs. And so there's a sort of a little balance here to try and keep a 3-detector network running for as long as possible in the mix. The proposal right now is floated at extending the run through till around the end of May 2025. Round numbers, May 2025, and starting O5 around June 2027. So that's roughly where it is. This week, we're supposed to have something that we have consensus across the LVK, and we're going to be sharing it more broadly to actually find out other opinions as well.
Okay, time for one or two more questions.
So you talked a lot about binary mergers, but I was wondering about gravitational waves from core collapse supernovae. Could you comment on the distances to which we might detect that in these various planned upgrades?
Yeah. So core collapse supernova are challenging. First of all, let's focus on what we know about, well, let's start with the rates. So rates, okay, 1 per 100 years in our galaxy, you know, count outwards. So you have to start getting out fairly far to start getting a few per year. So that's our first challenge, just in terms of supernova. But then the real second one is knowing anything about the strengths. And the uncertainty in the strength of gravitational waves from supernovae is really very, very large. Potentially, by the time we get to 05, we might be able to see some of the more extreme models out to, I don't know, tens of megaparsecs, but that's the really extreme ones, right? And even the most recent, the nearby supernova, 23, no, 20, well, not that one, the 23 one, the one in 23 in May. May 23, there was a nearish by, not as nearby as 1987A, but getting closer. We were observing at that time, and we have got an analysis to put a constraint. So that's actually going to start to constrain some of the more extreme theories. And so, but we really don't know so well, so it's going to be a challenge.
I think we will hear more about that in the afternoon. Actually.
Yes.
Okay, so we're exactly on time, and now there will be coffee outside of the auditorium here, and we should reconvene at 10:55. So the next speaker is Alessandra Bounanno from the Max Planck Institute for Gravitational Physics in Berlin. And the title of the talk is up here, Addressing the Challenge of Precision Gravitational Wave Astronomy. Please.
Okay. So first of all, thank you to the organizers for giving me the opportunity to speak at this interesting symposium in Stockholm. So you heard from the previous talk by Patrick Brady of the great success of the LIGO and Virgo and Kagra collaboration in the last 9 years. So he showed also this plot that represent all the black holes and the neutron stars that we have discovered, represented in the stellar graveyard. So you heard about, of course, the very first event, 150914, the first binary neutron star discovered the 17th of August 2017. More recently, just a month ago, the first neutron star black hole with a black hole squarely in the so-called lower mass gap. The largest binary black hole observed today, the 21st of May 2019. And finally, a couple of events, actually 2 of them, for which the secondary mass, it's as a mass which perhaps is too large to be the mass of a neutron star and too small to be the one of a black hole formed from a collapse of a star. So in this brief presentation, I want to highlight the role of the waveform models in the discovery and the interpretation of the signals, discuss also some of the recent theoretical advances in this field, and also I want to address the fact that, as you will see, with upcoming runs and also future detectors, the sensitivity will improve, and together with improvement in sensitivity, we have also to improve the waveform models, otherwise we will be dominated by biases. So, in fact, let me start by saying that in the case of gravitational waves emitted by binary system, we have the luxury that we can predict in advance the signal, solving the Einstein equation, as we will see in a moment. And because of that, the best way to detect the signal is using match filtering or signal processing. I have here just an animation to show you that what is done. You have the data in black in the lower panel with perhaps a signal. The template is correlated with the data and is maximized. So one computes the signal to noise ratio maximized on the parameters of the binary. And if that at some point when the template matches the signal, goes above a certain threshold that has been set based on the noise of the knowledge of the noise of the detector, we can claim a detection. And in order to build this bank of templates, we need many templates of the order of several hundred thousands of them. And when we do also inference analysis after the detection, we need to produce millions of these signals, and we need to do it very quickly. So again, let me emphasize that the reason why we are interested in the waveform is because they contain information of the source that has produced them. And just visually, so this is a waveform for two black holes going around each other on a quasi-circular orbit, known as spinning. From the frequency evolution, you learned from Patrick's talk earlier on that the frequency is increasing over time. As you can see here, we can infer the masses of the system. From the amplitude and the masses, we can reconstruct the distance where the source was with respect to the Earth. From the time of arrival, the amplitude and the phase at the detectors. Since there are more than one detector, we can reconstruct the sky location. And if we see modulations in the signal, you can see the difference between this one and this one. Modulation in the amplitude and the phase, we can conclude if the two bodies were moving on a circular orbit or an eccentric orbit, or whether the spins of the black holes were, for example, precessing along the direction of the total angular momentum. Moreover, if the binary contains matter, so in form of a neutron star, there is a new parameter, as we will see later, which describes the tidal deformation of the neutron star due to the tidal field of the companion. And this again imprints as an imprint on the waveform. And when you compare with a binary black hole with the same masses, you can see that going toward merger, there is an accumulated difference in phase. And that's the way in which we can actually extract this information of the tidal deformability and learn more about the neutron star. Finally, we can also build a waveform in a theory of gravity which is not general relativity, in an alternative theory. And again, by matching this waveform with the data and comparing with what the GR waveform do, we can probe the theory of gravity. Okay, so in order to build these waveforms, we have to solve what in the community is called the two-body problem in general relativity. And this basically means that we have to solve the Einstein equations, which I wrote here, which is complicated because the equations are non-linear due to the fact that mu nu and r depends on the metric g mu nu and its derivative in a non-linear way. And the best way to solve this problem is using numerical relativity, which means to solve this equation on supercomputers. However, this is the slow way because to compute the two black holes going around for just 15 orbits, it may take between a few weeks and 6 months, depending on, for example, the mass ratio in the binary. And this is the reason why numerical relativity is restricted to a certain region in this parameter space here. So luckily we have other approach that we can use to solve the Einstein equation, which it's an approximate way, but it's fast. So the oldest method is called post-Newtonian theory, where you expand the Einstein equation and the radiation in powers of v over c, v being the relativistic velocity in the binary. And because of the viral theorem, this is also intertwined with an expansion in Gm over Rc squared, where m is the total mass of the binary. And so post-Newtonian theory is limited to large separation and slow motion. You can also expand the Einstein equation in powers of the Newton constant. This is called the post-Minkowskian approximation. And is valid still for large separation, is in the weak field, but you don't expand in the velocity. So you can describe fast motion, and in particular, for example, scattering or high eccentricity in the binary. You can expand the Einstein equation in powers of the mass ratio. So you don't expand in the velocity on the gravitational field, so you are completing the strong field. But this expansion makes this method applicable only in the case in which you have a small body going around a large body, like the extreme mass ratio in spirals, as we will see later. Then on one side, we can put this method together, and in particular, at the moment, actually, this effective one-body theory has many bits based on post-Newtonian theory. This approach also provides phenomenological answers based on physical results to describe the mergering down. This is a time domain waveform again, which is then improved by using numerical relativity simulations. On the other hand, we can also build waveform directly in frequency domain. They are called inspired mergering down phenomenological waveforms, which are built through a combination, a fit of effective one-body theory, post-Newtonian, and numerical relativity. And this two plot is just to show you that if you were plotting for a particular value of the binary parameters, the amplitude of the waveform in frequency domain up to merger and also the derivative of the gravitational wave phase, these are very simple functions, so you can build closed form frequency domain expressions. So this is also a very successful waveform model, especially because it's very fast to generate. Okay, so just one slide to give you a little bit more information about how we calibrate this model to make them very accurate, both on the effective one-body family and the phenomenological one. You start from, in this case, an effective one-body waveform which is not calibrated to numerical relativity. You can see that after almost 56 gravitational wave cycle, you accumulate a dephasing, and then you include some parameters in the waveform, like higher order post-Newtonian correction that are not known today. You feed them to numerical relativity until the waveform agree very well. And then you repeat this for many numerical relativity waveforms. So this is an example of the calibration that was done against the 441 numerical relativity waveform that were used from the simulating spring spacetime collaboration, which has the most accurate code today to produce a long simulation with very small errors using a pseudo-spectral code. And this is just to show you in the binary parameter space of the mass ratio and some combination of the spin of the black holes where the numerical relativity simulations are. And then basically you repeat this procedure for each of these dots, and then you extend the model everywhere else. And these waveforms were used to upgrade the waveform models used by the collaboration, SUBNR, IMR Phenom, another family of effective one-body waveform, which is called TOB-RISAMS, for the ongoing run 04. I want also to mention, quite importantly, that because of the large number of numerical relativity simulations that we have today, people have also, in the last few years, built interpolations of these numerical relativity waveforms. They go under the name of numerical relativity surrogate models. And they are the best waveform that we have, the most accurate one. The only thing is that they are limited in the region where numerical relativity is available. We will see an example later. Okay, so the waveform model are used then for the match filtering searches for low masses for binary neutron star. This is just the projection of the template bank in the mass parameter space. We use, LIGO Virgo uses post-Newtonian templates, and for neutron star black holes, we need to use templates that incorporate the mergering down, because we are sensitive to that part for binary black holes and neutron star black holes. Okay, let me give you some highlight now how the waveform played a role in the interpretation of some of the results. So this is the 1908-14 binary. So it was highlighted before that this binary had the peculiarity that the mass of the secondary is quite peculiar. We don't know if it is a neutron star or a black hole. I want to highlight that for this event, the mass ratio was quite large, of the order of 10. And the more substructure and complexity you have in a binary, for example, an asymmetry due to masses and spins, the richer is the gravitational radiation. So this is illustrated in this visualization where the event was visualized. So this is the total actually radiation. And now decomposed in harmonics. This is the L equal to M equal to. This harmonics becomes more and more important as the binary reaches merger, because the amplitude of these modes is proportional to the velocity of the binary divided by the speed of light. So if you go 1 second before merger, now you barely see the L equal 5, M equal 5 in this visualization. And now more concretely, by actually including the effect of the spin precession in this system and the higher harmonics, as you can see here, the posterior distribution for the secondary mass could be, it becomes quite tight, and the LIGO-MIGO collaboration could actually achieve this very good measurement of the mass of the secondary. Otherwise, as you can see, if you don't include this effect, the posterior will be broader. Another event that I wanted to highlight is the one of the largest binary black hole. This is a simulation that was done in our department under the leadership of Harold Pfeiffer. Was a very short event, as you can see here, due to the large masses. And now I want to show you the results using the waveform models. So for the extraction of the parameters, the masses, the primary and the secondary, you can see now that the posterior distribution has some difference between the EOB-NR models, the phenom, and here also the NR surrogate was used because of the very short actually waveform, so it could be applied. And this event was also interesting for the spin content. So what we generally measure is the projection of the spin along the direction perpendicular to the orbital plane, and also the projection of the spin on the orbital plane, chi-p, that give us information about precession. And there is some signature of precession if you compare with the prior, which is here in black. Again, there are differences between the models, but these differences are not majors because at 90%, which are these 90% confident intervals, these posterior distribution actually overlap with each other. But now over time, the statistical error is going to decrease, while if we don't improve the waveforms, the systematic is going to show up. So we have to do some work in order, in the future when the statistical error will decrease because the detector will become more sensitive, we have to do something in order to improve the waveforms. Okay, in fact, let me tell you something about the accuracy of these waveform models. And one way to, actually the best way to assess the accuracy is to compare to numerical relativity. And the quantity that we generally compute is what is called the mismatch. So the mismatch is 1 minus the overlap between two waveforms. If this mismatch is 0, means the models agree very well with numerical relativity. So in this plot here, you see the comparison of the two state-of-the-art models that are used by the LIGO and Virgo and Kaga collaboration against the 1,500 spin precessing waveform from the XXS collaboration. And what is plotted here, so with this axis here, is the mismatch, average mismatch on the signal-to-noise ratio, and maximize on the mass of the binary between 10 solar masses and 300 solar masses. These vertical lines are the median of the distribution, below 1% or slightly above 1% for the IMR phenom. So where this numerical relativity simulation sits in the parameter space? So the one that are used to calibrate the model, which are the aligned spin, the blue one in this plot, can go up to mass ratio 20, although there are many gaps, as you can see here, and they don't go to very large spins. The 1,500 illustrated used for this plot here are the precessing simulation here in color. As the color goes to yellow, they are largely highly precessing, and they are however limited up to mass ratio 4 and up to spin 0.8. So in fact, in the region of parameter space where we don't have numerical relativity, the only way we can assess how good are these waveforms is that we try to compare the waveform with each other. If they agree, perhaps we think that they are a good representation of the signal. Otherwise, if they disagree, this is not a good news. Although, of course, the best will be filling more of the gaps of numerical relativity. Okay, but let me give you more a concrete example of what does it mean if I pick, for example, from this plot, a case in which the mismatch was 12% or 2%. What does it mean in terms of parameters, impact on the recovery of the parameters? So this is an example with a signal-to-noise ratio of 20 with O5, so the next run. And a numerical relativity signal was injected with a mass ratio 6, highly precessing. And so the injected value is here. The model with 12% of disagreement with an R would predict a primary mass which is off from the injected value at 90% credible intervals. But even more importantly, for the recovery of the spin parameters, the 12% of mismatch would lead basically to a measurement of the precession, which is quite off from the injected value. And this is quite important because if you if you were interpreting the binary as a mild precessing, you may miss the formation scenario, since, for example, a binary forming globular cluster are more likely to have highly precessing spin than binary in fields. So this is quite important if you want actually to interpret correctly the signals. Okay, let's move forward. So the big frontier for modeling is eccentricity, because until now, both the template banks and also all the analysis done by LIGO and Virgo and Kagra have used quasi-circular orbit waveforms. And this is a visualization of the flux emitted by two black holes going around each other, initially at an eccentricity of 0.3. The flux is mainly in the direction perpendicular to the orbital plane, but it's also in all directions, and the plane is moving because the primary spin is actually precessing, so you can actually notice that by the fact that the radiation is actually not always in the same direction. And in the bottom here, you see the H plus and H cross strain and the complications due both to precession and also to eccentricity. And in fact, from the point of view, let me talk now about the advances on the numerical relativity side. So I showed you before some coverage of the numerical relativity. In the last few years, that coverage has been expanded for quasi-circular precessing binaries, and also more recently for eccentric spin precessing binary black holes. This is very important also to build this NR surrogate. If we increase the number of numerical relativity at our disposal, we can build more these interpolated families that are the most accurate one. So there are many numerical relativity groups, and I want to highlight here the expansion of the parameter space in the last 4 years achieved by the Simulating Extreme Spacetime collaboration, going from the blue region, which is the one I was discussing just a few slides ago, which was ending at mass ratio 4, now expanding up to mass ratio 10 and even 20, although still with some gaps. Not yet at very large value of the spins. For the coverage of spin precessing eccentric binaries, which is, as I said, very important to have both effects, this plot here is showing the parameters of this new numerical relativity simulation with eccentricity up to 0.5 and mass ratio 4 for different values of the spin of the primary and also the spin of the secondary. Again, when you include eccentricity and precession of the spins, you have very complicated waveform, as you can see here. So this is numerical relativity. I also wanted to highlight these results from the UT Austin for eccentric waveform, and this result from the Cardiff group that also have focused to highly eccentric quasi-circular orbit binary systems. From the modeling point of view of eccentricity, we have the first models. Unfortunately, eccentricity, but still a line spin. Not precessing, but is already a step forward. And these models have been compared with numerical relativity only until now for low eccentricity, small spins. So again, you have a waveform where with the merger in down for different harmonics. You can use this waveform also to describe the dynamical capture. These are maybe more a likely event that we will have with LIGO and Virgo and Kagra, but it's nice to have the waveform to use them. And I wanted to highlight there have been several studies in the literature to infer eccentricity in the LVK population, in some cases also obtaining results, claiming actually some evidence of eccentricity for some events. Okay, so now let me move to actually binary with matter. As you can imagine, all the work at the interface between numerical and analytical relativity has been also extended to binary neutron star and neutron star black holes. So this is an example of a comparison of a waveform model with a numerical relativity simulation. These are snapshots of the simulations up to merger. The new parameter, as I mentioned at the beginning of my presentation, for binary neutron star black hole is the tidal deformability parameter, which depends on the equation of state of the neutron star, which is 0 for black holes, and measure the deformation of the quadrupole moment of the neutron star due to the external tidal field of the companion. So something quite interesting of the most recent waveform models is that this parameter is now included in the waveform model, not just as an adiabatic love number or a tidal deformability parameter, but dynamical one, because in fact this parameter can depend on time or on frequency due to the fact that there is a tidal force. The tidal force in frequency can match at some point during the evolution the oscillation frequency of the neutron star due to the normal mode of the neutron star. And so this fact is also quite interesting to have in the waveform models. Now, this waveform model have been used for the analysis of the binary neutron star and neutron star black hole by LIGO and Virgo. And I have only here I want to show the results with the recent discovery just came out last month that was mentioned by Patrick Brady. This is a simulation done by Tim Dietrich of the event. You see at the end the neutron star being disrupted by the black hole. So the masses were reconstructed for this event here, 230529. But I want to highlight, there was also a question before, that actually for this event, like also all the other events with neutron stars discovered by LIGO and Virgo, until now was not possible to put an upper bound on the tidal deformability, but not to nail down it. And in fact, the only way in which we can conclude that the system had a neutron star from a gravitational point of view is basically from the reconstruction of the masses. Because we are not actually measuring yet the tidal effects. For this event in particular, this was not possible because of the low signal to noise ratio, which was around 11-12. Okay, so now I want to show you that also in the case of neutron star systems, we can have systematics. I mentioned here, I want to show you the result from a paper by Kaufling and Tim Dietrich of a few years ago. So they considered O5, LIGO Virgo Cargo O5 run, 2027. And they assumed that during that time, I mean, based on the projection of how many binary neutron stars, maybe in the most optimistic case we can have, we could have of the order of 37 binary neutron stars. So they wanted to understand how well you can recover the radius of the neutron star. And so they stack all these events using one of the approximants with tidal effects. And after stacking many events, you get this posterior distribution in blue. But then instead of using this approximant, they take another approximant which differs by the way the binary black hole baseline is built. The tidal effects are the same, and they get a systematic here. Or they change the way in which the tidal effects are incorporated, keeping the same binary black hole baseline. And so what they found is that although in principle you could measure the radius of the neutron star with an accuracy of 250 meters if you were stacking all these events, due to systematics actually you will get a systematic error twice as large. So this really calls to an improvement of these waveform models for the upcoming runs, not to talk about the next generation detectors. And also the numerical relativity waveform needs to be improved if we want to use them to calibrate the models. Okay, so now let me move to the last part about the next generation detectors. So it was mentioned in the previous talk that we expect to have new facilities on the ground in Europe and in the US. There will be an improvement in the sensitivity by 1 or 2 orders of magnitude. And also the sensitivity will become much better at low frequency, which will allow actually to see with this detector black holes with larger mass with respect to what we are seeing today, up to a few thousands of solar masses. And because of the improved sensitivity, we can go at a much larger redshift. Now, if you look at the number of events that we could see with these detectors, just in 1 year, with a signal-to-noise ratio larger than 100, current prediction would say 10,000 of binary black holes. And at this larger signal-to-noise ratio of the order of 400 binary neutron stars. The signals are going to be also much more complicated in some cases, because if we can see, for example, these 1,000 solar mass black holes, we might be seeing what people call intermediate mass ratio in spirals, where the mass ratio is of the order of 1,000, and so the dynamics is much more complicated. These are snapshots at 1 Hertz and 10 Hertz. So it was mentioned we will have LISA in the next decade, since it has been adopted as mission, is now under construction, adopted by ESA just at the beginning of this year. And LISA will open the frequency, the observation in the frequency range of the millihertz, and the sources will be complementary to ground-based detectors. In particular, we will see the signals represented here coming from the coalescence of massive black holes. And depending on the mass of the black hole, the signal-to-noise ratio can reach more than 1,000. And these are the tracks of different harmonics from extreme mass ratio in spirals, so a small black hole going around a large black hole. So the signals are going to be loud, they are going to overlap, they are going to be there all the time. So these are not transients like for ground-based detectors. The data analysis is going to be much more complicated, called for what is called in the literature global fit, where all these events have to be detected and then subtracted all at the same time. And I wanted to make now 2 examples of what happens with this next generation of detectors if we don't improve the waveform models. So you can take the example like Gravitational-wave 190814, which had a mass ratio 10, but consider now that it's highly precessing, which was not the case, at least we didn't find that it was highly precessing. And now let us consider the 2 state-of-the-art models today. You can also reverse and use one as a template, the other as a signal, doesn't matter. We cannot use actually for this test a numerical relativity waveform because this event is very, very long. So let's inject one of these models as a signal, recover the other as a template. 405, A sharp, and XG, this will be the signal-to-noise ratio. So we are interested to do cosmology, so recovering the distance. And this is actually the true value. And these are the Poisson distribution for 05 and A sharp. And this is where XG will be, which will miss completely the true value. But even more importantly, the sky localization. So this was the galaxy where the event was, and the sky localization is completely off. One can consider another example, which is less asymmetric, mass ratio 6, but high total mass. So these are the signal-to-noise ratio in this case. And you can see that even for 05 and A sharp, now the Poisson distribution are completely off the true value. So this again calls for better waveform models, otherwise we cannot use these events to do cosmology and extract the Hubble-Lemaitre parameter, because we will not be able also to recover the redshift. Okay, the last example I wanted to make is different, is for LISA, is a test of general relativity. So one of the most interesting things that we can do with LISA, with large signal-to-noise ratio, is to do a spectroscopy of the ring-down stage. So this study considers a numerical relativity signal in general relativity, which is injected, and then to recover the signal, one uses a model where the frequency and the decay time are not just the one of GR, but one is adding a deviation. And this is the result. So for this event, the signal-to-noise ratio was 228. GR is here, and the recovery is off. And so if you were using this waveform model that we have today, we would have a false deviation from GR in the quasi-normal mode frequency and decay time at 90% confidence interval. And there have been also many other papers in the literature that have looked at this false, actually, deviation of general relativity with current waveform models. Okay, so let me now, I have just 2 slides to conclude. The accuracy of the waveform model needs to be improved by 2 orders of magnitude. Numerical relativity simulation also would need to become more accurate for binary black hole, and also in particular for binary with matter. not only we have to extend the waveform to generic orbit eccentricity, but especially for next generation of detectors on the ground and in space, this binary could be in accretion disk. They could be also perturbed by a companion. We could have effect due to gravitational lensing, illustrated here in the case of LISA. You see the impact on the waveform if you have a lens of these different values of the mass. The color waveform is lens and the uncolor is actually black here. And so in order to improve them, one, of course, way in which people are working now is to actually embed these perturbative results in the effective one-body approach and phenomenological approaches in a more effective way and also all together, because until now they were mainly based on one of these approximants, which was post-Newtonian theory. Also, the calibration to numerical relativity should be more effective, should be extended to spin precession and eccentricity. And I have to say there is a new community actually to people working in high-energy physics, which has decided to help people working in two-body problem. And I have brought new tools actually to tackle this problem in the so-called post-Minkowskian approximation. So in fact, at the moment, the frontier is to go in post-Newtonian theory to 5 pn, which is this line here. And in post-Minkowskian theory, we are almost at 4 p.m., and the frontier will be this 6 p.m. So let me skip a moment this slide. I want to say that the big, actually, important results that we need, if we want to take advantage of the extreme mass ratio in spiral science, is also to go to a second-order gravitational self-force. This plot here illustrates the improvement of going from first order to second order compared to a numerical relativity simulation with mass ratio 10. So you can see the improvement here, the dephasing if you were using first order, and how well it compares with numerical relativity if you were using second order. However, these results are only available for non-spinning quasi-circular orbit, and in the next 10 years they have to be extended to the generic case of eccentricity and spin precession. So let me end. I think I went over time, right? Okay, so maybe I can just say, highlight again that the work at the interface between analytic and numerical relativity has been essential to detect the signals and infer unique information. With this wonderful new observation that we will have in the future with large signal-to-noise ratio and many, many events, we really need to do more work in gravitational wave modeling. And I emphasize at least 2 orders of magnitude will need to be improved just for GR in vacuum. And all physical effects in the waveform needs to be there unless we want, otherwise we would make wrong scientific statements. Okay, I want to thank my department and in particular the agencies and the LIGO Virgo Kaga collaboration and the other collaborations. Thank you very much.
Thank you very much for this great talk. It's time for a few questions. Ariel.
So actually I think it was your last bullet actually, about given all the difficulties you've been describing, what are the prospects of going beyond Einstein, or what are the prospects of testing theories beyond GR?
Yeah, so first of all, I have to say that in the last few years, there have been also quite interesting results in numerical relativity where people are evolving binary black hole in some alternative theory of general relativity. And also on the side of analytical calculations. So we start to have the first example of IMR waveform in this beyond GR. But I think you are asking, unless in fact we take into account all the non-GR effect, yes, it's true. I mean, this deviation from general relativity are expected to be very small. And so we have to be careful that we are not, basically confusing them with other kind of effects. I mean, it's possible. It's just that we have to do a lot of work. Unless, the deviation from general relativity is very large, but this is very unlikely, I think.
Okay, more questions? Yeah.
Can these templates use matter for the very bright foreground sources in LISA? the bright galactic double white dwarf binaries?
You mean for the galactic? So I don't know if I understood the question. Just 1 second. I want to put back this. So are you referring to the not the foreground? I mean,
effectively the things like the verification binaries. So where you're trying to
oh, for the verification binary, these are just basically monochromatic signals.
Well, but not necessarily if they're eccentric, for example.
Yes, yes, but I mean, you have multiple harmonics if you want, but you just need the leading order, terms they are not chirping, right? So in that sense, but you can have different harmonics indeed. But they should be the easiest thing to detect. In fact, it's claimed that the verification binary will be detected in the first maybe 6 months already.
Okay, time for one more question. Okay, yeah.
So you seem to advocate these approximate methods. And so what is the hope for numerical relativity to be able to fill in this gap in between the time from now until the next generation of detectors? Is this nothing we can hope for at all?
Well, I think numerical relativity, even if, sorry, am I going backward or? Sorry, 1 second. I wanted to go back to this plot I was showing. So you saw in one of my slides that, this slide here. So there is an improvement, which is quite actually spectacular in the binary parameter space going up to, in the last 5 years, up to mass ratio 8, as you can see here. However, these simulations are still, limited in length. So even if you were covering this part of the parameter space, you would need still to hybridize this waveform with some of these approximants I was discussing before, so that they can be long enough that you can measure, you can observe a binary black hole of any mass. Because if the waveform is not very long, then you are limited to see only black holes which have a mass larger than a certain value. Normally 60 solar massing in total. But you can see how large is the parameter space. I mean, this is just mass ratio 20. And also, you want to go to very large spins, for example. And here there are actually, it's not easy for numerical relativity to cover that regions. So that in the next 10 years, we can cover, the entire parameter space for LISA and Cosmic Explorer and the Einstein Telescope. I'm not sure we can do that, but certainly, we will be able to do much more than what we have today. Maybe arriving to 10,000 of these numerical relativity waveforms. So today, if you put together the two, are 4,000.
Okay, I think we need to go on. So let's thank Alessandra. So the next talk is by Stephan Rosswog from Hamburg and Stockholm, and the title is Gravitational Waves and More. What can we learn about extreme physics from neutron star mergers?
Okay, thanks a lot for the invitation to beautiful Stockholm. As Klaus has said, let me see how that works with the pointing. Okay. I want to talk about what we can learn from double neutron star mergers. And these are actually really wonderful systems because they are related to lots of different questions that I think are very important. To name just some of them where one could learn something from compact binaries, one could actually learn something about dark matter. As we have just heard, we hope to learn something about strong gravity. One of the things that is now mainstream, which was an exotic idea, say 20 years ago, is that there are actually also sources of heavy elements. And this was one of the major science questions I'm not really sure how that works, identified at the beginning of the new millennium. Then there are still questions related to gamma ray bursts that we still don't understand. We can hope to get a good senses about what binaries of black holes and neutron stars we have in the universe. And as we've heard, one can hope to do cosmology with them. So I've drawn here a little sketch, absolutely not to scale. And at the point 0, there should be, there is the merger. And one thing that you can hope to learn something about maybe dark matter is the early inspiral stages, or just before the merger, because what you mostly do is you assume your binary is in vacuum, but in nature maybe black holes are embedded in dark matter clouds, and this could actually leave some interesting effects on the orbital evolution. If you then go just directly prior to the merger, just a couple of milliseconds before that, there's this nice diagram, and the binary merger would move through this diagram roughly along this line. And you would have something like 17 minutes to reach from 10 Hertz frequency to the merger. But the point where you actually have tidal effects is only once the separation is very comparable to the size of the stars. And at that point, you hardly have any time left. You just have fractions of a second. But nevertheless, this carries potentially very important information, just because the tidal deformability is very sensitive actually to the equation of state and to the ratio between mass and radius. And what you can hope to learn from that is really how nuclear matter is behaving, and behaving at a couple of times the nuclear matter density that you have in a big nucleus. Now, if you think about just the time after the merger, so many neutron stars may not be massive enough to lead to a prompt collapse, and then you will have something like a central remnant that is surviving. And this remnant will oscillate at frequencies of kilohertz. And at that point, this will be made of material that has something like 10 to the 15 grams per cubic centimeter, so maybe 5 times nuclear matter density, and actually also temperatures of something like 10 to the 12 Kelvin, which means this is something like 100,000 times hotter than what you have in the core of the sun. And potentially you could see effects from phase transitions and so on. And this is actually one of the major science drivers behind the Einstein telescope. Now, some friends working more on the equation of state, they like to show this so-called QCD phase diagram, and also just to illustrate what neutron star mergers could do there. So the main idea is that you have density on the x-axis and you have temperature on the y-axis. And nuclei are somewhere just above 10 to the 14 grams per cubic centimeter, but essentially at 0 temperature. Neutron stars, the old ones that we can see, they're also effectively essentially at 0 temperature, but they can have a couple of times higher densities. And at some point, going to higher densities and temperatures, one expects to have a transition from hadrons to quarks and gluons. And neutron star mergers actually can really cover a very broad range in this diagram. Temperatures really essentially from 0 to maybe 10 to the 12 Kelvin or so. Densities going up to, well, maybe 10 to the 16 grams or so once you're collapsing to a black hole. And also in terms of the proton fraction, they start essentially from nearly only neutrons. But since you reach these very high densities and temperatures, weak interactions also become very fast. And you can actually produce also a very broad range of electron fractions there. Now, one more interesting thing here, just milliseconds after the merger, is whether there are some fast parts in the ejector. So we now know, just from GW 170817, that there are some fair amount of ejecta. But the question is there or how many is there of material that is maybe above half the speed of light? And this could be actually very interesting because these ejecta, they have something like a homologous structure, which means the fastest parts are leading the ejecta. And some parts could actually be so fast that the neutrons that are in there can avoid being captured by nuclei. And that means you have something like a leading layer, which could be decaying neutrons. And from that, you would expect to have something like a precursor to the kilonova, maybe an hour or so after the merger. But at the moment, there are lots of question marks, but this could be something interesting. Something else that one would expect from such ejecta is they would produce like a gamma ray burst, something like an afterglow, but not fully relativistic, just, well, Lorentz factors of maybe 2 or something. and maybe this has actually already been observed in the aftermath of GW 170817. Now, one big question still, where we still don't have, I think, a convincing answer is, how do you produce actually those Lorentz factors that you need for a gamma ray burst? There you need something like Lorentz factors of about 100. There has been, in the last few years, quite some progress, I would say, from the numerical simulation side. There are outflow type structures that you see, but they're very far away at the moment from those Lorentz factors of 100. They are something like 50% or so of the speed of light. Now, one question that is, of course, also very interesting here is the nucleosynthesis. I've just mentioned this stuff that gets ejected. And in the late 90s, we saw, well, we did the first calculations here of how the nucleosynthesis would look like. And the thing that was particularly convincing was that you could produce the elements in this platinum peak very nicely. And it's called platinum peak because platinum is sitting at a nuclear number of 195, but you also have gold in that thing. And this was something that has been always terribly complicated for supernova models. And that gave us some confidence that this may be actually something really interesting and maybe relevant, because I think it's the most convincing way to produce this type of material. And if you now look at how nucleosynthesis calculations look there, then you see you start, can I point here? You start close to the drip line. You go to this very heavy region here, so beyond those magic numbers at 126. And what you end up with is material that in particular produces this platinum peak, which is the one over here, but doesn't produce terribly much below that. But if you now change, this was for an extremely neutron-rich matter, so this is something like the original matter that you have in a neutron star, but if this is processed by these high temperatures, then you would get a different nucleosynthesis. So if you do the same thing for something like 0.3, you're not really starting at the drip line here. You're not actually going beyond these magic numbers here at 126. You're not going to these very massive nuclei. And when you decay back, you produce some material, well, which doesn't produce this third R process peak. But if you put them together, those two components, you're actually very close to the solar system abundances. Now, of course, things have become way more complicated. We know about different ejection channels. And we know, just as was illustrated just in those two movies, the results are very sensitive to the neutron richness of the material, which also means, well, we have to get neutrino transport right, which is a very difficult problem because it's really a 7-dimensional problem that you have to solve there. And of course, the results, they may also depend on which binary is actually really merging. So can we believe that we have seen our process? I would say, yes, we can be actually pretty sure that we've seen a broad range of our process material. One argument is this transition that one has seen from blue to red within a few days. The other thing is just a decay of the bolometric light curve, which fits very nicely exactly what you would expect from a broad range of our process elements. And there have been some claims about lines, the most popular being strontium, but I think that is much harder, and I think we know much less about really individual elements that have been produced there. Now, if you want to model the kilonova emission, that has also become a bit more complicated. So this is a little sketch like what you would expect if you have on the if you have here a neutron star surviving. That looks quite a bit different from the case where you have either a black hole from the beginning or a prompt collapse. And the major reason is that this neutron star, this will emit something like 10 to the 53 ergs per second in neutrinos. So something like 20 order of magnitude more in neutrinos than the sun is emitting photons. And that material is really then driving winds, which become more proton-rich. And if you also want to produce a gamma ray burst, you also have to get a jet that gets out through this at Lorentz factors of 100. And then apart from this geometry issues, there are lots of things like that the atomic physics is not terribly well known. And at least at later times also, you run into technical difficulties that you can't assume, for example, that you have local thermodynamic equilibrium anymore. Okay, so now if you think of this as trying to model this, then I think it's pretty obvious that it would be really the goal to have different messages being modeled in a halfway consistent way. Ideally, of course, gravitational waves and electromagnetic waves, and in a really ideal world, hopefully also actually neutrinos, but this will be very, very difficult to detect. And one thing that is actually worth keeping in mind is that all of these electromagnetic signals that you see, they are coming from something like 1% of the binary mass that is ejected. And that means if you try to model this complicated thing, you have to get this 1% really right to be sure what you should look for. The other thing that is interesting in that context here is you have very different physics involved for the gravitational waves. You talk about strong gravity, you talk about dense matter, you talk about high magnetic fields. While for the electromagnetic emission, you need to have the atomic physics right. You talk about many, many orders of magnitude less in terms of density. You talk about radiative transfer and so on. But it's, of course, also beautiful because they tell two different sides of the story. Say, for the gravitational waves, you really learn what the source is doing, while for the electromagnetic waves, you can learn a lot about the astronomical environment. Yeah, so that was part of the motivation behind also developing a new tool. And this is a code that is called SPHINX, which stands for Smooth Particle Hydrodynamics in Curved Spacetime. And when we started the project, it wasn't clear to us how complicated it would become. So I can't say terribly much about how it's really working, but in case you're interested, there are 5 very long papers that you can go through where all of the details are laid down. So you may now wonder, well, there is good numerical relativity tools around. So why would you want yet another tool? And why do you want a Lagrangian tool? And the answer there is the existing numerical relativity tools that do hydrodynamics, they are all Eulerian. That means you evolve your fluid on a mesh. And these methods are really good for many things, but they're also struggling with a couple of things. Like in particular, they are struggling in getting ejecta correct. And one thing that you sometimes see in simulations is something like this. Where are we? This stuff here that you have these winds around the stars, but this is purely artificial. This is really a numerical entropy production that produces winds. So it's really important to get this 1% right, and therefore there are all kinds of effects that we would try to avoid. Now, how did we do this? So we, for some reason, decided not to start with any toolkit, but we really actually decided to go really for empty editors for Emacs and VI. So it really looked like this one here. And my partner in crime here is Peter Diener from Louisiana State University. And there we're actually sitting at LIGO in Livingston. And it was really a little bit like this beautiful song from REM that you're trying to push an elephant up the stairs. So what we decided to do, to go for just some space-time evolution that is known to work, because our Eulerian colleagues have pioneered this for many years. So that is one thing we wanted to go for. But then we wanted to evolve the matter with particles. And that involves also that the particles in the mesh, they have to talk to each other. And in an actually very accurate way, otherwise many things really go wrong. And this was the hardest part of the whole project. And we are now at algorithm number 18 to do so. And now I think we are converged. This is now beautifully working. For the spacetime evolution, we're doing things essentially the same as our Eulerian colleagues are doing. So we're slicing the 4-dimensional spacetime into 3-dimensional hypersurfaces that are evolved forward in time. And then we have the real metric as the metric that we have on the spatial slide. And then we have 2 extra components. One thing is the so-called lapse function, and the other thing is the shift vector. And once we know these things, then we can put together the 4-dimensional metric. And to evolve this, to some extent, it has some similarities to magnetohydrodynamics in the sense that you have evolution equations, but at the same time, these evolution equations should fulfill constraints that should be preserved all of the time. So this is similar to in MHD, where you shouldn't create numerically magnetic monopoles. So you would want to have the divergence of B being equal to 0. The equations look terrible and are cumbersome, but they work very nicely and actually robustly. And the part that is now new is trying to do numerical relativity with particles. And here the idea is that you take the fluid, you represent the fluid by particles, and they can just move around. Each particle is carrying something like a smoothing kernel with it, and what you can do with these smoothing kernels is you can calculate, for example, pressure gradients. So these are things that you need to evolve your fluid. And the reason why this is, at least in Newtonian case, a very nice thing is because you can construct your evolution equations in a way that you have exact numerical conservation of mass, energy, momentum, and angular momentum. That is nothing that you can do, to my knowledge, in a Eulerian method. So then we started here with the GR version of that, and you can do this actually starting just from a Lagrangian, and then you need, of course, the energy momentum tensor, the four velocities, and you need to know the metric. Then you have to choose what variables do you want to evolve, and we went for the canonical momentum and the canonical energy, which are nice variables coming from the Lagrangian. And then how do you get the evolution equations? You get them from kind of nice physical golden principles. You use the Euler-Lagrange equations and use the first law of thermodynamics. And then you get equations that look like this. And the nice thing about this is it's, of course, just as you would have expected, momentum, energy, and baryon number conservation. And they actually look pretty similar to the Newtonian equations. So there's a first part here, which are things like pressure gradients. So this is just the hydrodynamic part. And then you have the second part here, which involves the energy momentum tensor and derivatives of the metric. And this is the part that is coming from gravity, obviously. So major capabilities here, I think in terms of gravitational waves, there's not much more that we have to add to what the Eulerian methods can do, but I think the things that we can do on the hydrodynamic side, they are important for these multi-messenger things, especially for the electromagnetic emission. And one thing, apart from a couple of other very nice things, is that we're not bound to something like a computational volume. And just to illustrate this a little bit, the current world record with the Eulerian method to evolve the ejector of a neutron star merger can evolve them to something like 130 milliseconds. Now, this is now an experiment with Sphinx, and there the simulation just started like a normal numerical relativity simulation a couple of milliseconds before the merger, but then we really evolved the ejector out to 2 years compared to these 130 milliseconds. And also for these 2 years, there's no technical reason for this. It's just at some point you realized you're not simulating all the physics that would be in there, but you could actually evolve this for even much longer. And also to say this, and of course the densities drop dramatically from above nuclear matter density to very low densities. Okay, so after that, now I want to show one of the first applications of this new tool, and this is a scenario. It's not entirely new, but maybe it's not, it hasn't been given enough attention. So, and the standard scenario usually is that you look at binaries where you have no spins or close to no spins. And the reason for that is many of the in-spirals, they can take hundreds of millions of years. So there's plenty of time for potentially spinning neutron stars to spin down. So the Haas-Taylor pulsar has 300 million years as an in-spiral time. But the time when you can spin up the stars, that is just those last fractions of a second here before the merger, is tiny. So you would not expect a major spin up from there. But of course, there are special places in the universe where this could be different. And one of those places are globular clusters. And they are very nice because in their cores you have densities that are many, many orders of magnitude larger than what you have in the solar neighborhood. So you have lots of opportunity for close flybys, for collisions, and so on and so forth. And also, if you look at the neutron stars that you see in globular clusters, if you just go through tables of the known neutron stars, then you see of those neutron stars that are in globular clusters, more than half is spinning at millisecond periods. So there are lots of them that seem to have had, well, maybe different evolutionary paths. And I talked to our stellar evolution expert, Thomas Tauris, then, and he came up with this very nice diagram. And this is now a way how you could produce a system that starts initially like a normal evolution, that you have a neutron star together with a non-degenerate star. At some point, the non-degenerate star evolves, becomes bigger, transfers mass. This is then visible as a low-mass X-ray binary system and is spinning up the neutron star while consuming the other star. And what you end up with then is that you have a millisecond pulsar together with a white dwarf. But then you're in a globular cluster, and there are plenty of chances for flybys. And if you then have a neutron star flying by, then chances are pretty big to kick out the white dwarf. And then you have a system where you have one neutron star that is very rapidly spinning, and the other one is, well, probably close to non-spinning. And Thomas went through all of the known systems and estimated that, well, out of the emerging neutron star binaries, something like 5% or so could be actually those cases where you have 1 millisecond pulsar. And then the question is, of course, okay, how different would such systems be? How different would their signatures be? And this is what we tried to explore in some recent work here. And there we started with binaries where we just have one spinning neutron star. And since we wanted to focus on the effect of the spin, we chose equal mass systems. And we chose two different equations of state, one which is a bit on the soft side, one which is a bit on the stiff side, and one which is maybe something like the best guess. And we used spin parameters of 0.5 for this one star. And you see at this spin parameter, the spinning star looks actually substantially bigger. So this is the XY plane. In the XZ plane, you see the reason for this, just because it's rotationally pretty seriously flattened. And if you then look at how this would look like, so this is the orbital evolution of those guys, and you immediately see the guy that looks more like a lentil here. This one here, this is the spinning star. And now it gets shredded, and I said it's an equal mass system, and you see you produce just this one big tidal tail. But it's an equal mass system. So in a sense, what you produce here looks relatively similar to a system where you have a pretty big difference in the masses that are involved. And the question is now, well, what can you expect there? One thing that is actually, I think, interesting is that the encounters with the spinning guys, they're substantially less violent. So maybe if you just ignore the units on the y-axis here, and focus maybe on the black line. So this is the peak density in the non-spinning case. And there you see you very massively compress the neutron stars, get very big bounces back, and then reaching up to, well, close to twice the initial density. And if you look at the same system, same equation of state, but with the difference being the spin, which is this orange curve, then you see these are substantially less violent. And therefore, also the post-merger gravitational wave amplitudes actually are less large for the spinning case. And if you look at how efficiently you emit energy and angular momentum, you also see, well, this is consistent with this and producing, well, a less efficient emission of these quantities. This also carries, of course, as most things, an imprint of the equation of state, and this is more pronounced if you have a softer equation of state. Now, if you think about kilonovae and you're wondering about ejecta, if you look just at the dynamic ejecta, just as you would probably guess from the shape here, is they eject more. And you see all those colored curves here below are the non-spinning cases. The spinning cases are those here, and just roughly they eject something like 1 order of magnitude more material in terms of dynamic ejecta, so the stuff that becomes unbound on millisecond timescales. There's also different ejecta, which are released on longer timescales, and here the consensus is this is something like 30% of the initial disk mass. And also there, for the disk masses that we can easily determine from the simulations, you also get up to something like a factor of 2 or so more for the spinning cases. That means you would produce a particularly bright kilonova. I don't want to go through all of the details here that we've looked into. You would expect a particularly bright kilonova, and because of this tidal tail, it would be also, there would be a lot of red low YE material involved here. Another thing that is interesting to look at is, again, if you have a look at how this looks at the end of the simulation, not all of that material in this tidal tail is unbound. Some stuff is just flung out to high eccentricities, kind of parked in the orbit later and then falling back. And if you try to estimate the luminosities coming from these fallbacks, this is what is shown here as this m dot in, I think this must be solar masses in per second. And then you also see here you have for the spinning cases, you have later fallback and you have longer fallback. So you would expect particularly bright and particularly long fallback. And if you take this together with the less efficient gravitational wave emission, then you have at least something which is interesting for someone who is thinking about gamma ray bursts, because that would naturally produce an engine that has a prolonged engine activity. And there have been now several, well, I call them here enigmatic gamma ray bursts being detected, and these are bursts that show a bright kilonova, but also produce a long gamma ray burst. And this is pretty puzzling still at the moment, and I don't think anyone has a super convincing answer what is going on there. But I think with these prolonged central engine activities, maybe just one part of the story is going in the right direction. Probably we need other parts to come to these long timescales that they see here. And with that, I'm at my summary. So I hope I could show you some interesting examples of extreme physics that are related to compact binaries and their mergers. I presented very briefly a new simulation tool, really tuned for calculating multi-messenger signatures of binary neutron star mergers. And then I showed this, renewed scenario, let's call it like this, that non-negligible fraction may actually contain a single spinning neutron star, and that has a couple of interesting things in it. And with that, I'm stopping here.
Thank you for keeping it. Okay, yes.
Thank you for the very nice talk. So, yeah, I was interested about, so you showed the ejecta evolution in your Eulerian and your code. You can now go until like 2 years or something like that. So I was wondering how the computational costs compare between like those Eulerian equations and yours.
That's a very good question, but also a very difficult one to answer, because say in the Eulerian case, you just have meshes, and you do your spacetime on the mesh, and you do your fluid on the mesh. That's just one time. In our case, we have an adaptive mesh for the spacetime and the fluids, and there are 3 parts of it. Like you have a time step restriction for the spacetime, you have a time step restriction for the particles, and you have to get this mapping back and forth right. So it's really, I can't give you a single answer to that. So I think we may gain, for example, for cases where maybe you have a very stiff equation of state, where the space-time curvature is not ridiculously large, that you get away with a not so big, not so fine grid, just because you don't need it. And then the question is, how many particles would you want to have? And depending on which part of what the astrophysical question is that you're asking, you need to have different resolution in different parts. And if you really want to resolve these fast ejecta, for example, then you have to put as much as you can into the particles. And then it's hard to compare, because Eulerian methods cannot really do this.
Thanks a lot.
Okay.
On the business of the spin mergers, I mean, how different are they from what our expectations from 2017 GFO? I mean, are they different enough that they could be confused with supernovae and hence missed by current searches, or?
I don't think so. So you have seen those light. So you're talking now about how different.
How much brighter could it be? I mean, you say they're brighter.
They're brighter, and just from the masses. If you just take this as a proxy at late times, what you get as the luminosity is just the nuclear heating rate times the mass. And if this is up by factors of a few, say not this full order of magnitude, because this is just the dynamic ejecta, but it could be brighter by a factor of 3 or 4 or 5 or something like that.
Cool.
Yeah, so I have 2 questions also on the single spin mergers thing at the end. So the 5% fraction of the mergers, would that be 5% of the entire binary neutron star merger population, or 5% of the subpopulation merging in globular clusters?
That would be 5% of those guys that merge, but not restricted to globular clusters. So just 5% of those that you can potentially observe. 5% of those guys.
So, and then also about that population, what like mass distribution, or what would you expect for the different neutron stars if you are able to
I think
say that?
I think those 5%. This is based on those 23 double neutron star systems that we have. So take this with a grain of salt. Just saying it's not a negligible thing. It could be an interesting contribution. Sorry, the question was mass distribution.
Yeah. So like since you have mass accretion.
Exactly. So the kind of like say that the textbook answer to that is if you want to spin up the neutron star to something like a millisecond period, you need to accrete something like, I think, 0.24 solar masses, which is a fair amount of matter. And that also means that different from what we have done in this first study, the spinning star should be substantially more massive. So this is something that we haven't looked into yet, and also maybe related to this question of the long mass transfer rate. One of those things that one of my first ideas was when I saw this big tidal tail. There are some stars that are particularly enriched with actinides. These are called actinide boost stars, and one thing was, well, could this maybe be the source? But they're seen so early in the universe that this long mass transfer that you need to produce the system. So this is not a good thing. But the punchline, something like 0.25 or so, would need to be accreted to reach this.
More questions? Let me ask you one. How sensitive are your merger simulations and to the equation of state and the details, especially at high densities?
They are pretty sensitive to this, and this is of course something that we are about to explore. But since the whole technology is still pretty young, we haven't done all the stuff that has been done with different technologies already. But it definitely makes a big impact. Also, these fast ejector that I've briefly mentioned, there you see also an impact. A part of this is really shock-heated material, and if you have a very stiff equation of state, you produce substantially less shock, so you're much less likely to have a substantial component of this fast material. While if you have a very soft one that bounces back substantially, then you can get much bigger effects from that.
That also is the case for the nucleosynthesis?
We are not yet there, because in the current stage we don't have neutrinos in it. This is something we've just began to start, but we have zero results there. But I guess yes, because also this shock-heated material has much better chances to be higher in electron fraction because it was substantially heated. So I think it has an impact on essentially every part of the signal.
Okay, good. If no more questions, then it's time for lunch, and the lunch is being served outside here, and that's the case for all participants. So it's just go out and grab something, and then we reconvene at 1:30.
Welcome back again after the lunch. My name is Ariel Goobar. I think I forgot to say that the first time around. So I will be chairing the afternoon session. And upon the request, I think, of Samaya, by the way, who will be giving the talk now, there will be a show of, we'll walk by the room where the press conferences are held when the Nobel Prizes are announced. So people who are curious how the room looks like, just only seen online, you will have the chance to walk by the room and take a look. So that will happen if Peter, well, we will hear in connection with the next break. So no, stay tuned for that, people walking in that direction. Without further ado, I just give the floor to Samaya to talk, and everyone sees the title right. So welcome, Samaya.
Thank you very much. And can you all hear me okay? Yeah, great. So I'd really like to thank the organizers for inviting me to give this talk, and I hope in the next 30 minutes or so to really outline the challenges and the opportunities that are emerging from multi-messenger astronomy with gravitational waves. And so, without further ado, so in the last 8 years, over three science runs, we have now observed at least 90 binary black hole mergers as well as binary neutron star mergers. So shown here on the schema, where on the y-axis you have the masses in solar masses, the horizontal axis doesn't have any significance. The blue and the orange bubbles here represent the black holes and the neutron stars that we have observed in gravitational waves, where the pink and the yellow bubbles are representing those black holes and neutron stars respectively that were previously inferred from radio and X-ray observations. And as we heard this morning, we have started our 4th science run with the 2 LIGO detectors and the Virgo detector joining just a month ago, and there have already been 105 significant candidates that have been released to the wider public. And so there are a few things that I would really like to point out. Number one, that we are actually, sorry, I'm going to go back. We are actually uncovering this fundamental diversity in the fundamental properties of these black holes and neutron stars. Secondly, there remain open questions as to what are the nature of some of the progenitors as well as the remnants of these neutron star binary mergers, as well as the existence of previously hypothesized mass gaps. And thirdly, as these have been the research and focus of my research in the last 18 years or so, I'm going to be focusing on these neutron star black hole mergers, where at least one of the objects has matter in the form of a neutron star and may emit electromagnetic radiation due to the delayed matter outflows from the complicated merger of these systems. And I'm going to be specifically zooming in to our one binary neutron star merger, GW170817, that we have observed in gravitational waves, as well as in every part of the electromagnetic spectrum. This remains our only multi-messenger binary neutron star merger, but this allowed us to actually pinpoint for the first and only time where a gravitational wave merger is actually happening, as well as allowed for several firsts. As we've heard, the first gravitational wave standard siren, Hubble constant constraint, the first association of a binary neutron star merger with a short gamma ray burst, one of the first discoveries of a kilonova, as well as the astrophysical sites of our process heavy elements, as well as the first tests of the speed of light and gravity with a neutron star binary merger event. And this one neutron star binary merger is really impacting several diverse fields in astronomy and physics, as you can see here. And this is really thanks to the advances in gravitational wave detectors, time domain astronomy, as well as what is happening in computational astrophysics, as well as in big data and machine learning. And so in the next part of my talk, I'm really going to only have the time to focus on a few of these highlights, such as nuclear physics, cosmology, as well as high energy astrophysics. So, and I'll be talking about work that has been done with my group in Amsterdam, as well as in large gravitational wave and electromagnetic collaborations, as well as a whole host of individuals, as well as groups located all over the world. And so what are gravitational waves? Well, they're the perturbations in space-time curvature. They're sourced by these time-varying quadrupole moments, and our measurable is this gravitational wave strain, this dimensionless h of t, which has this important 1 over distance to the source dependence. And this is important when we talk about actually increasing the sensitivity of our detectors, as well as using these systems as standard rulers. They have 2 polarizations, H plus and H cross. These act as transverse tidal fields. And this tidal stretching and squeezing is how these gravitational wave detectors, such as LIGO and Virgo, they're essentially measuring this tidal stretching and squeezing of space-time by measuring these 2 polarizations, which are weighted by the quadrupolar antenna function. And in the frequency band of our detectors, the most numerous sources are these binary neutron star mergers and binary black hole mergers. Now, in order to actually detect and extract information from our gravitational wave strains, we need to have very accurate models of what our dimensional wave strain looks like in the form of these gravitational waveforms broadly speaking, comprising these three phases: the in-spiral, the merger, and the post-merger ring down. What I'd like to stress is that in the frequency band of our ground-based detectors, for systems of a few solar masses, we are most sensitive to the in-spiral phase, tracking essentially thousands of cycles and with the duration of the signal lasting on the minutes. And so this in-spiral at lowest order is driven by the chirp mass. This is simply a combination of the two masses of the object and is modeled extremely accurately, as we heard this morning, using the post-Newtonian approximation in general relativity, where v here is the characteristic orbital velocity of the system, and parameters such as the reduced mass, the spin orbit, spin-spin coupling occur at higher post-Newtonian order and can cause significant beating and modulation of the wave strain. And this will impact how well we can actually infer parameters such as the masses and the spins. And for instance, finite size effects, so that are encoding information about the internal structure of the orbit through this tidal deformability parameter, that is essentially the ratio of the induced quadrupole over the external tidal field of the companion, appear at higher post-Newtonian, at 5 post-Newtonian. And this gives us very important information about the physical size of the object, specifically the radius as well as the mass. And so once we have these models in hand, we can actually then match filter or cross-correlate our detector output with template banks of 10 to the 5, 10 to the 6 of these gravitational waveforms, and not only detect, but then actually infer the gravitational wave parameters from using random stochastic sampling techniques at the moment, such as Markov chain, Monte Carlo, and nested sampling methods. One thing I'd like to stress is that typically this analysis, depending on the complexity of the waveforms that we're using, can take day to weeks to months timescale. Okay, and so of course this is quite important when we talk about actually sending out information for electromagnetic and other facility follow-up. And so there are two challenges that I'd like to stress for the community. Number one is inputting more physics as well as environmental information potentially into the waveforms. So looking at systems with more mass ratio, with different mass ratios, misaligned spins, really improving the accuracy as we heard this morning. And then secondly, leveraging machine learning such as simulation-based inference techniques to actually speed up the analysis. We're seeing by several orders of magnitude and by different groups. And this is really impacting how we can potentially send out more accurate and more precise information for electromagnetic follow-up. And so when we talk about electromagnetic follow-up, what's critical is how well we can localize these systems in gravitational waves. So these interferometers are quadrupolar all-sky antennas. They typically have very poor angular resolution, and in order to reconstruct where the event is happening in the sky, we typically have to use triangulation of the arrival times of the signal, as well as some information about the quadrupolar antenna function of the detectors in order to localize the system. So in the case of GW170817, we were able to actually send out our first alert at 5 hours after the event. The sky error was at the time 28 square degrees. I remind you that the moon is 1/4 of a square degree, and the distance to 40 plus or minus 10 megaparsecs. Okay, so with this information in hand, observers were able to actually then cross-match this gravitational wave volume with known galaxy catalogs, either ranked in mass or in light, and essentially identify, and several groups were able to actually identify a bright blue flash that occurred at 11 hours localized to the galaxy NGC 4993. Okay, and so I'm showing here the transient, as you can see with this red cross here, appearing that did not appear in archival images several months earlier. And this was done by the 1 meter 2 hemisphere telescope collaboration using the SWOPE telescope in Las Campanas. And this initiated essentially this unprecedented ground and space-based campaign involving 70 teams, over 100 instruments, and over 3,000 co-authors. Several of you are actually in the room here. And indeed, where I spent most of those exciting few months. And one thing I'd just like to stress for the community, the next challenge that we're seeing in subsequent efforts of following up gravitational wave mergers is that actually, indeed, that bright blue flash for GW 170817 ended up being a bona fide binary neutron star merger. But this is not the case that, as we're seeing for further out events with larger sky areas. The necessity is on us as a community to really characterize these other astrophysical and variable transients. Now shown on the right here, this figure I think really denotes the full panchromatic beauty of those first years of observations for GW 170817. Here you have the spectral flux density as a function of the time after merger in different wave bands. And what I'd like to stress is that you can see that there are essentially two groups of observations. And what made, I think, this data set so incredible was that it really at 0th order agreed with the predictions that there should be two different types of outflows that are responsible for the two electromagnetic counterparts that we heard today in Stephan's talk, the kilonova as well as the short gamma ray burst. Okay, so the kilonova, oh yes, the movie's working. The kilonova is this rapid neutron capture nucleosynthesis powered transient, which is thermally emitting in the ultraviolet, optical, and infrared on the day to weeks timescale, and allowed for the discovery of one of the sites of heavy elements. So this is really encapsulated in one of my favorite movies of the event, taken by the Very Large Telescope at ESO, at the European Southern Observatories, where you can essentially see this typical black body blue photospheric emission evolve to longer wavelengths, become dimmer, as well as actually show these broad line absorption features, which are indicative of the creation of these heavy elements. The second counterpart, and the second discovery was, of course, that binary neutron stars are the progenitors of short gamma ray bursts. We were able to have many insights into the nature of the relativistic jet. I'm just going to highlight one of the results that will impact something I'm going to say later on for cosmology, which were the observations taken by the Very Large Baseline Interferometry a year after the event at two different epochs, essentially measuring the proper motion of the centroid of the source, which suggested that the jet actually had structure, both radially as well as angularly, and that we were able to actually infer the inclination angle to the binary to 15 to 25 degrees. And so I'll return to this. And of course, we heard in Stephan's beautiful talk this morning how important and imperative it is to actually really model the outflows of microphysics, which is extremely challenging given the different microphysical processes there, as well as the different time scales and length scales. And there are many open questions still remaining from GW 170817, despite having this enormous wealth of data, such as what is actually the central engine of the jet? Do we need black hole formation for the jet to launch? As well as why was this kilonova essentially so blue? And this brings me on to the step that many groups, including my own, are really working on, is how to actually build a systematic and comprehensive framework to actually analyze jointly and interpret both the gravitational wave dataset with the electromagnetic datasets for strong signal binary characterization, as well as in the future for population. So in order to say something about the demographics, ecology, and census. And this is non-trivial. because the data sets obviously involve lots of parameters. Number two, there are unidentified or not well understood degeneracies between some of these parameters, as well as thirdly, this question of actually not having at our disposal a coherent model of the in-spiral merger and ring down using numerical relativity as well as hydro and neutrino transport, etc., as we heard this morning. And so an example of an analysis tool that was developed in my group by my former PhD student Hert Rijmakers is GEMMA, a gravitational wave and electromagnetic multi-messenger analysis, which essentially allows one to actually go from the binary properties to actually the light curves, which are shown in this schema. So essentially we are ingesting on the gravitational wave side the binary properties, the masses, the spins, as well as the tidal deformability, and mapping these out to the outflow properties using semi-analytical formulae, which in themselves have some errors. So we have different outflow properties for the different masses as well as the velocities of the different components. And then we can map this out to the different light curves using semi-analytical light curve models. And indeed, we are now implementing this into Redback, an open source inference and simulation tech toolkit that Nikhil Sarin has developed for all transients, actually. So please go and check that out. So I'm going to just highlight 3 results that I think are incredibly exciting. In the case of GW 170817, so we heard this morning from Patrick how the gravitational waves and the gamma ray burst allowed us to actually constrain the speed of gravity in light to 1 part in 10 to the 15. The second is that neutron star mergers are a unique probe of the QCD phase space, shown here in temperature as well as density, allowing us to perhaps actually map out the transition from hadronic matter to quark, gluon plasma using our neutron star mergers, both their gravitational wave and electromagnetic signatures. And what I'm showing here on the right here is the mass radius plot for neutron stars. And underplotted are all the various theoretical predictions of equations of state. And in this purple horseshoe are the 50 and 90% confidence intervals for our first multi-messenger analysis, including GW 170817, our second binary neutron star merger, GW 190425, as well as 2 rotationally powered millisecond pulses that were observed by the X-ray NICE emission as well as radio observations. And you can see that we're essentially preferring more stiffer equations of state as well as already ruling out some equations of state. And several works have shown that actually really to hone in on the equation of state, we need about 50 or so very strong of these kind of multi-messenger events to make progress. Now, the third result I'd like to highlight is one of the most basic endeavors in astronomy is actually measuring the distance out to objects to actually map out the universe's expansion history. And in the case of GW 170817, we were able from the 1/distance measurement to have a measurement of the distance, and from the optical counterpart to have a measurement of the redshift, and actually to constrain Hubble's parameter that expresses basically the energy density components of our universe. So what I'm showing here is the probability of a function of the Hubble constant, and the orange is this GW plus the optical redshift measurement. And in blue, what I'm showing is the GW plus optical redshift plus that radio measurement of the inclination angle, allowing us actually to break the degeneracy between the GW distance and inclination angle in the GW data sets, which allowed for an improvement of a factor of 2 in the measurement of H0. And what is particularly exciting is that gravitational waves are providing us with an independent measure of actually measuring Hubble's parameter, where at the moment there is this very intriguing and exciting tension between low redshift and high redshift measurements of the Hubble constant. And so this is shown here in orange, the 50 and 90%, using the relative standard candle measurements, Cepheids and supernova, as well as supernova 1As, to that derived from the cosmic microwave background using Planck measurements. And so we have shown that we need about 50 of these gravitational wave plus optical redshift measurements to reach about a 2% precision, which may potentially allow us to start actually resolving perhaps this tension. And in the case if we include radio observations, if they're very strong, we're talking just using a 1/√n explanation of about 15 of these events. So perspectives. And so looking forward, looking forward, we already have electromagnetic facilities that are operating today, such as the Zwicky Transient Facility, which is with its field of view of about 45 square degrees, that is allowing us to actually tile these wide gravitational wave localizations, as well as the Black Gem Telescope in the Netherlands. And of course, excitingly, this decade, in the next couple of years, we will be looking at having the Vera Rubin Observatory, as well as the Square Kilometre Array in the radio, which will really allow us to have this multicolored movie of the dynamic universe, no longer having single snapshots, but really being able to follow time domain astronomy and our dynamic and variable skies at different wavelengths. Coming to the gravitational wave detectors, we have moved in this era from individual objects to statistics, as we heard from Patrick, and shown here is this global network as a function of time for these different observing scenarios. This is where we are today, and the rates I've listed here are consistent with the fact that we have with what we are seeing actually in the fourth science run. And of course, moving forward, what is particularly exciting is what will be happening in the next decade. So with regards to upgrades to LIGO in the form of LIGO A#, as well as with Virgo, as well as the actual construction of these next generation observatories, the Einstein Telescope and Cosmic Explorer. And so shown here is the instrument sensitivity as a function of frequency for the current as well as projected noise curves for these gravitational wave detectors. So in blue, you can see the noise that was achieved by the third science run by LIGO. In a bit darker blue is the one projected for this fifth science run, A+, A# here in the dark blue, so a factor of 2 sensitivity improvement, and then this factor of 10 sensitivity improvement by the Einstein Telescope, both in the broadband as well as moving to lower frequencies. And this impacts the science that we will be able to do, not only with this this improvement of 10 in sensitivity relating to a factor of 1,000 in volume and rate, but also to actually being able to have information about the post-merger of our neutron star binaries, as well as more information about the in-spiral of these signals. And so the Einstein Telescope, the original concept is that we have a single observatory that's built 200 to 300 meters underground and will comprise 3 nested interferometers with 10-kilometer long tunnels. This 10 times better than design sensitivity. And in the US, we heard that there are plans to have the Cosmic Explorer, which will comprise 2 detectors, 40 kilometers and 20 kilometers with 10 times sensitivity, and will be operating in a global network with the European Einstein Telescope. And so shown in this plot is the cosmic reach of the Cosmic Explorer as a function of redshift and the total binary mass. And so you can see the Cosmic Explorer design sensitivity here as a function of different signal to noise ratios, so 1,000 and 100. And shown in yellow here are the binary neutron stars, red neutron star black hole and white binary black hole mergers that we should be able to observe. Essentially all of the events that are happening in the universe, and we'll also be able to observe new populations such as population 3 black holes, as well as speculative primordial black holes coming from the inflationary early universe. And so shown here is GW 170817 with Cosmic Explorer and Einstein Telescope. It should have a signal of noise ratio from 32 of what we had to 1,700. Okay, so we're talking about sky resolution of about 10 to the minus 3 square degrees and really precision measurements on the mass. And the science case for Einstein Telescope really and Cosmic Explorer really is a plethora or treasure trove of science cases both on astrophysics as well as fundamental physics and cosmology. I don't have the time to go through all of this, but happy to talk offline about some of these, such as dark matter, black hole properties, etc. And there are two things I'd really like to emphasize. Number one, like Cosmic Explorer, the Einstein Telescope's reach is really astounding. Okay, so shown here on this infograph of JWST, one of the most exciting discoveries has been that of newly identified high redshift galaxy candidates. And what I'm overlaying here are how far we can go at the moment with current gravitational wave observatories and how far we'll be able to actually observe back with instruments such as the Einstein Telescope, really going beyond the epoch where the first stars would have been formed. And the second thing I'd like to stress is how many of these kind of events we can expect. So shown here are the numbers of binary neutron star mergers per year that one can expect if we do have this very promising and optimistic scenario of having a network with one Einstein Telescope and 2 Cosmic Explorers. I think this number is simply astounding. We've heard today about a couple of hundred of compact object mergers, but when we're really going to the 100,000 of these kind of events per year, it does take one's breath away, I think, yes. And so in this talk, I have talked really about the high frequency end of the gravitational wave spectrum. You'll be hearing in the next talk about the nanohertz regime, where there are many exciting new projects that are coming online, including on the millihertz regime with the LISA space interferometer, this comprising these 3 spacecraft separated by millions of kilometers, which are cartwheeling in an Earth-trailing heliocentric orbit. And we will anticipate to have this another treasure trove or plethora of gravitational wave sources in this millihertz regime. So what I'm showing here is the spectral density, amplitude spectral density as a function of frequency. Here is the instrument noise curve here. And we expect to see both supermassive black hole mergers from 10 to the 4 to 10 to the 7 solar masses inspiraling and merging, as well as their ring down, these galactic white dwarf binaries shown in blue, the known white dwarf binaries shown with these red hexagons, as well as extreme mass ratio inspirals, as well as those binary black hole stellar mass objects that will actually move into the Einstein Telescope. And so just to finish, when we talk about the 2030s, we are really living this very, very transformative era or a change in our field. And I think I'd really like to impress how fast moving it is happening and how we do have to also change the way we are thinking on gravitational wave astronomy as well as multi-messenger astronomy. So in this donut plot, you can see the radial coordinators indicating the look back time or the redshift. The color lines here are showing the detection range of different instruments. In green, Einstein telescope, purple, Cosmic Explorer, red, LISA. You can see our beloved GW 170817 is here. And in yellow here are the expected binary neutron star mergers that we can see per day. Okay, the white are the stellar mass binary black hole mergers that we can see per week, and these are the binary supermassive black hole mergers that we have to be prepared to see per decade, potentially. Okay, so really, it's beautiful, but there's also just an incredible lot of work. So I'm so excited to see many students in the room because I really think you will be the ones leading the field forward in the next decades. And so it does require radical transformation. Multi-messenger astronomy will not just be talking about following up single sources. Of course, we will cherry pick those very, very loud events, those golden binaries, to do very detailed gravitational wave and electromagnetic studies, but also to talk about actually using these gravitational wave systems that we won't be able to observe their electromagnetic emission to probe large-scale structure and extragalactic astronomy. And with that, I'm going to end. So I hope during this day you have seen that I think gravitational wave and multi-messenger astronomy, the future is both very loud as well as bright. Thank you.
Thank you very much. Samaya, questions?
Can I ask? Thank you for the very nice talk and the overview. So I was curious that when the next generation, especially Cosmic Explorer and things are coming, will more information will be available if they observe like than right now we have, so that the EM follow-up within the first few hours or the first day has become more easier than right now. For example, we don't have mass, chart mass, this kind of stuff, right? So
yes,
the plan and the things.
Yes, so I mean, really, that will be the case. So, for instance, oh, let me just, sorry, yeah, here. In this table, what you're seeing is the number of events that one can actually expect to localize to 1 square degree, 10 square degrees, and 100 square degrees. But something like GW 170817, with 3 next generation observatories, the 2 Cosmic Explorers and Einstein telescope, will have a signal to noise ratio of about 1,700. Okay, so this is very, very different in terms of what we can say in terms of the masses, for instance, as well as the localization, as well as really being able to actually do detailed, sorry, I'm going back here, to really be able to do detailed precision astrophysics, okay? We will, because of the sensitivity curves that you can see here, we will have a lot more of the in-spiral accumulated. We can do, for instance, pre-merger alerts from the gravitational wave side that is already happening, but really here we'll be able to do it, on the half an hour to hour time scale, yes, as these systems are going by, as well as actually to see the merger and post-merger remnant, okay? And, yeah, I can't quite imagine sort of seeing that event, for instance, at a signal-to-noise ratio for, a couple of thousand, but really that ability. And then, of course, there's the question that we have to make sure our systematic errors, etc., are really under control, as we heard from Alessandra's talk as well.
Right. Thanks.
Any other question? Yes.
So I agree with you that this number is breathtaking. There's so many events, and there must be a lot of overlap. Like there's a few per minute or something. What is the clever technique for dealing with that?
So that's a great question, and so this is something that has recently just started happening in the last few years, is actually looking at how one can actually analyze basically overlapping signals, because we do expect them to be overlapping. I mean, very interestingly, Alessandra mentioned in her talk about the global fit problem that exists for LISA, where we already anticipate to not only have supermassive black holes lasting sometimes several months in BAM, but we'll have tens of thousands of these galactic white dwarf binaries, which will also contribute to a foreground, as well as some extreme mass ratio. We'll have a diversity of sources. And so similarly with Einstein Telescope and Cosmic Explorer, we're looking at the need to develop techniques that can really be able to deal with basically this popcorning. Yes, some of these signals will be loud and close to us, but the others will just be a general hum. Yes, and that is not a solved problem. So I think this is where we're going, and this is where we're looking to things like machine learning and AI coming in, because how do you deal with simply that number in terms of analysis? Yes.
So it looks like there's a lot of really cool science you can do with sort of order 10s to 50, say, EM, GW detectors. And given that a lot of these are going to be more distanced as the gravitational wave facilities get more sensitive, I was wondering, what do you need from the EM side in order to do science? Is it enough to get a redshift for the source, or do you need also like light curves or spectra, etc., to do that science?
That's a great question, and I didn't have time to really go into this. But for instance, if we want to talk about standard Sarin cosmology, we really rely on the redshift. Now, if we want to obviously have inclination angles at the moment, our VLBI measurement techniques are just permissible out to 100 megaparsecs or so. But if we're talking about a host galaxy redshift for cosmology, then that is possible in terms of optical redshifts as well as with GRB redshifts, or maybe from the radio counterpart. But if we want to do detailed nuclear physics, okay, then we really are talking about much, much closer events. But I think you're completely right to ask the question. At the moment, most of the other binary neutron star, black hole candidates that we have are detected at threshold. Yes, so they have much wider localizations, the depth is required by our facilities is much further, much more challenging, as we're seeing. But of course, as the gravitational wave detectors themselves increase in sensitivity, because we're volume limited, we will see more golden nearer events just consequentially. And also the network is expanding. So we have LIGO India hopefully coming online in the next few years. CAGRA is already online at a much reduced initial sensitivity at the moment. But as this network increases, the localizations will also shrink. So you're having the sheer number, localizations, and then the question is for EM facilities, it would be ideal, of course, to have follow-up, dedicated follow-up instruments that can deal with, I think, those events that are not as bright as GW 170817, as well as to really make sure that we can get spectra to do the confirmation, the identification there as well. So, I think, we'll see how it goes. I think in terms of the next 5 years will be very important, I think, in terms of pathfinders of where we're talking, where we want to be in the 2030s.
All right, we need to move on. So let's thank Samaya and Nissanke once again. Next, Chiara Mingarelli will be hearing. You have been hearing about this pulsar timing array, so we are really excited to finally get the full talk about it.
Behold, the black hole image. There's no electromagnetic counterpart at the moment, which is suboptimal.
It's the best electronic screen I've seen.
This is really ironic.
A lot of good sounds.
It's true. It's beautiful chirping sounds in the background. And we checked the slides before lunch and everything was fine. So we've all done our duty. Well, maybe I can just start by saying a few things. So there's now evidence for this gravitational wave background, and we think that it comes from the cosmic merger history of supermassive black holes. So it's been really interesting to hear all of the other gravitational wave talks with this beautiful chirping in the background now. Because we've heard a lot about neutron stars. And so for my talk, we're not looking at neutron stars as the sources of gravitational waves, but now we're going to turn them into gravitational wave detectors. And we can only do that for a special class of neutron stars, which are called millisecond pulsars. So the reason that we're really keen on using these millisecond pulsars as gravitational wave detectors is because their timing is so good. So we all know, more or less, that gravitational waves change the distances between objects. So as the pulsars are bobbing in this gravitational wave sea, the pulsars come closer to the Earth and then a little bit further away, and closer and then further away. And so what happens is that their arrival times, their really precise pulses, arrive at the Earth a little bit early and then a little bit late as the pulsar pulses come in and out and bob in this gravitational wave sea. So behold a beautiful animation showing you all of this, where the pulsars are coming closer and then further away. Ariel, can I demonstrate with you how a pulsar timing array works?
I've never been a pulsar before.
You can be my pulsar. Yes. Yeah. Be my pulsar.
All right.
So spin around. Yeah. Good. Your magnetic field is pointing towards me. Excellent. Good. So I'm seeing the flashes, and now as a gravitational wave comes, right, we get closer together, and then further away. And then closer together, and exactly. No, this is not physical. Thank you very much, Erika. Wonderful. Excellent. We'll have a little clip on YouTube. Right? It said it was alcohol-free beer at lunch, but now I'm not sure. Okay, good. So while we're still sorting out the technical details, let's see, what else can I tell you about pulsar timing arrays? So the pulses are advanced or delayed, but if you see that in just one pulsar, that could be anything, right? Because the pulsars are really far away from the Earth. They're 3,000, 4,000 light years away, and there's this interstellar medium between us and the pulsars. And so then, of course, if your pulsar pulses are smeared out by dispersion delays through this interstellar medium, you can have some signals that arrive earlier and some that arrive later. And this looks a lot like a gravitational wave background. And so how can you be sure? I think that it's going to come soon now. The electromagnetic counterpart here is working, but there's a time delay. It's somehow strongly lensed. Okay, wonderful. And so, right, we got through a little bit of the talk, which is wonderful. I'll just show you this figure. I love this figure. Because I made it with my dad, who's the second Mingarelli. Yes. So this was this paper was a result of a disagreement over a bottle of wine at Christmas. He's a mathematician, and I was telling him about how we, can ignore the perturbations of the gravitational waves of the pulsars because they're out of phase, and all the perturbations at the Earth are in phase. So if you imagine a gravitational wave washing over the Earth, it hits all the signals at the Earth at the same time. This is called the Earth term. But as it's transiting the galaxy, it also hits the pulsars, right? And it'll be at different points in the binary's evolution. So those signals are all out of phase. So I said, don't worry, Papa, we can ignore that. It's fine. And he was like, I don't understand what you mean. You have to prove this. And I was like, well, I did it numerically. And then I showed numerically that it's, very small. And he was like, well, what about all of these other infinite values? And I said, okay, Papa, we can prove it mathematically. And it turns out, you'll be happy to know that it's a straightforward application of the Riemann-Lebesgue lemma. But if you don't want to know that, which I didn't think many people would, I said we needed to put a really nice figure in our paper so that people would cite it. And so I came up with this figure based on the Moore et al. 2014, but I added some nice-looking labels and other additional figures. So we're going to focus here on pulsar timing arrays, and we had some nice talks about LIGO and LISA, which are very cool, but in my opinion, not cooler than pulsar timing arrays. I mean, who else has a dance like that, right? I think I've proven my point. All right, so this is my super cool animation where we have our galaxy mergers. The supermassive black holes are in the centers of these galaxies, And as the galaxies merge, their central supermassive black holes start to merge. So here these black holes are 10 to the 8 to 10 to the 9 solar masses, and they're separated by a milliparsec, which is basically the size of our solar system. A milliparsec is basically the size, is the distance from the Earth to Pluto, on average, for any astronomer in the room. So this green space-time fabric is, coming out, going out in all directions, and some of those gravitational waves make their way towards the Milky Way galaxy, where Ariel is spinning around beautifully, bobbing in our gravitational wave. See, now it makes all sense, right? Now we understand what was happening. And the signals are red-shifted and blue-shifted, or equivalently arrive a little bit early and then a little bit late. And so it was a really interesting conversation that we just had in the last talk with Samaya about how, we might not be able to distinguish the individual sources if there's too many of them, right? That this is an unsolved problem. But for pulsar timing arrays, this is exactly what we want to see. We want to see this incoherent superposition of signals. We're looking for it. And in fact, we spent 15 years looking for this gravitational wave background. And so the signal that we now have evidence for comes from the cosmic merger history of supermassive black holes. Now, contrary to what we heard before, in our detector and pulsar timing array detectors, we're so far in the in-spiral in terms of towards minus infinity that our sources spend about 25 million years in the pulsar timing array band. So they are not transient. We are anti-transient. We're very long-lived, many PhD student lifetimes are in one of these inspiraling signals. In fact, we think that there's about 1 million slowly spiraling supermassive black hole binaries in our lowest frequency bin. Now there can be hundreds of thousands more at higher frequencies. We think that supermassive black holes are the primary source of the gravitational wave background, but there could be other things that contribute to the gravitational wave background. Our detector just responds to low-frequency gravitational waves, and those could be primordial, they could come from cosmic strings, they could come from lots of theories that people are writing about now that create these low-frequency gravitational waves. But how do we actually understand where the signal comes from? Well, what we actually do, it's kind of hard without the TV, I'm totally in the wild today, is that we look at this cross-power spectral density between pulsar A and pulsar B. So what does this mean? It means that I go to the Green Bank telescope and I have pulsar A and pulsar B. And I time, and by I mean my very good radio astronomer colleagues, they wouldn't let me near one of their telescopes, but they go and they time a pulsar and they get a timestamp. They look at it for 30 minutes, they find an average time of arrival, and then that is the time of arrival for that day. They go back 2 weeks later, they do the same thing, I get a timestamp. And eventually you get this whole time series of data from each one of the pulsars. Now the gravitational wave signal induced by the background should be the only signal that's the same in all of these pulsars. The noise is totally different. So what we do is that we cross-correlate all of these data streams. You take your one time of arrival that you measured at Arecibo, and then you cross-correlate it with one at the Green Bank telescope, and then one from Effelsberg, or one from another completely different data stream. You do this huge cross-correlation, and that's how we find the signal. So there's two parts to the signal. One is called the overlap reduction function, which gives you the Hellings and Downs curve that we've made a lot of fuss about recently, and I'll go into that in the next slide. And then the second part is this characteristic strain. So before we looked at all of these waveform images, and that is just the strain. The characteristic strain is the sum of all of the strains at a particular frequency, and we add them in quadrature. That tells us what the amplitude of the gravitational wave background is. All right, so what is the Hellings and Downs curve, and why do we care? So this is part 2 of our interpretive dance, but I've got this one, don't worry. So when your pulsars are separated by a small angle at the sky, the pulsar pulses arrive early and late in sync, right? They're kind of bobbing together like this. However, when they're separated by larger angles on the sky, because gravitational waves are quadrupolar, they'll be anti-correlated, which means one arrives early while the other one arrives late. They have the same amplitude, but the timing is different, right? So they arrive early and then late, and then early and then late. And so your signal is strongest when they're positively correlated over here, and then it becomes weaker, and then it's strongly negatively correlated, and then in the infinite of having, in the limit of having an infinite number of pulsars, out pops this beautiful curve called the Hellings and Downs curve. Now, the Hellings and Downs curve tells us that what we're seeing is for sure gravitational waves. It's a quadrupolar-like signal that you can't get from random astrophysical processes that are happening to your pulsars. And unfortunately, we can't turn our pulsars on and off to find out, if something went wrong. We can't reboot them. We just have to use the data that we have. So it's important when we look for the signal of the background that we have not only this amplitude, or the characteristic strain, but that we also have this quadrupolar type correlation when we cross-correlate our pulsars. All right, so now you saw what the Hellings and Downs curve should look like. Now this is a measurement of the gravitational wave background. And this is, I still can't believe that we're finally showing it, because when I was a graduate student, it was always 5 to 10 years away. Anyone else that did gravitational waves as a grad student knows the tagline, like, when will we find it? 5 to 10 years, or like grant timescales, and that was the punchline. It was actually 5 to 10 years away when I was a grad student, which is nice. So this is the measurement of the gravitational wave background, and Sarah Vigeland was the corresponding author for this paper. It was a huge Herculean lift to find the signal, but just briefly, here you have your prediction in black. That's the Hellings and Downs curve. You have the measurement here in blue, and then no gravitational wave background would give you nothing. You would get 0 cross-correlation terms. And so what does this mean? Well, it took us 2,211 pulsar pairs to find the signal, and those came from 67 pulsars. The reason that we went from the 12.5-year to the 15-year data so successfully to find this signal was because we added 21 more pulsars. And the signal-to-noise ratio in our detector scales as the number of pulsars, only the square root of the time. So even though we only had 2.5 years between the 12.5-year data set and the 15-year data set, the addition of these 21 extra pulsars really boosted our ability to find the Hellings and Downs curve. We have base factors of 900 to 1 for the signal, and as we heard earlier, that we had between 3 and 4 sigma detections, depending on the statistic that you wanted to calculate. Okay, so now we have a gravitational wave background. We're pretty sure it comes from supermassive black hole binaries. Now what, right? So now what we're going to try to do is find out what astrophysics is happening around this cosmic merger history of supermassive black holes. What physical processes can we find in the background? So the first thing to do is to look at the strain spectrum, right? So here we have the characteristic strain, which is the square root of the other, of the characteristic strain squared that I was showing you. And then on the, I know I'm jet lagged. And then on the x-axis, we have the gravitational wave frequency. And so if we're assuming that your binaries are just driven by gravitational waves, then you have this scaling law here that goes like f to the minus 2/3. So this is from Finney 2001. However, if anything is slightly not gravitational wave driven, if you have stars that are interacting with your binary, or if there's gas, or if your binaries are eccentric, those physical processes are much more powerful, and they're much better at making your binaries merge than gravitational waves. But when your binaries are at very wide separations. So just to give you a sense of scale, 1 nanohertz corresponds to an orbital frequency of 30 years, right? So these are very slowly evolving, wide binary orbits, but they're moving quickly, but they're supermassive black holes. And so these things happen on very long time scales. So if you go an order of magnitude lower here in frequency, you can see that things like stellar hardening, these gas-driven torques, and eccentricity can make the strain spectrum turn over, right? This is terrible news for astronomers that like power laws. So the solution is a double power law, of course. So you can characterize it that way. You'll also see the green part is the amplitude of the gravitational wave background. And the amplitude of the background, in turn, depends on things like the merger timescales and the supermassive black hole masses. In fact, the characteristic strain squared scales is the Chert mass to the 5/3. And so we're really, really excited by black hole mass measurements. All right, so what did we actually find when we looked at the strain spectrum? So here's a measurement of the characteristic strain. And this black line is the f to the minus 2/3 power law that I just showed you. And this blue line is the best fit supermassive black hole binary model. So that looks really interesting. It looks like the signal, if it's just coming from gravitational waves, is higher, or is higher than it should be because it turns over. And so this could be our first sign at 2 nanohertz that something other than gravitational waves is driving the binaries to merge at very low frequencies. And so what else can we do now with this measurement of the gravitational wave background? Well, we can study the supermassive black hole binary population. And so here again is the f to the minus 2/3 power law. But you'll notice that this, minus 2/3 power law is really just a statistical average, right? You can't extrapolate it everywhere and everywhere. You can't take it to arbitrarily high frequencies. And that's because you have this astrophysical population of binaries, and they start to merge really quickly at high frequencies, and even more quickly for the larger masses. So the time to coalescence goes like the chirp mass to the minus 5/3. So your more massive binaries start merging, and in fact almost completely disappear at these higher frequencies. So here at low frequencies, where we have our strongest signals for the gravitational wave background, we have millions of simultaneously inspiraling supermassive black holes. But as we go to higher frequencies, you can see that by the time you get to 20 nanohertz, you've decreased the number of binaries and the frequency bin by 3 orders of magnitude. So you go from 1 million to about 1,000. And this is actually good news, because in the future, what we want to do is find the individual binaries. And as Samaya was saying, it's really hard to simultaneously model a stochastic background and also look for the individual supermassive black hole binary systems. So one solution to this is looking for binaries at higher frequencies. So this turnover, this exchange between the background and then individual binaries, looks like it happens at about 26 nanohertz. And my student, Andrew Casey Clyde, just published an article on this. And so these higher frequencies are becoming more and more interesting for us. But it's also difficult because we have our best sensitivity at low frequencies. And so now we might have to adjust our observing strategies to try to make sure that we can probe these higher frequencies where we believe the supermassive black hole binaries to be. Another way that we can access the individual binaries is by doing targeted gravitational wave searches. So when you do an all-sky search, you have really poor angular resolution. And in fact, that could be a problem for trying to identify the host galaxy. If your error box on the sky is, maybe at best 40 square degrees, there's a lot of galaxies in 40 square degrees on the sky. So some simulations show that the supermassive black hole binaries can be traced by these periodic light curves. And they almost have an equivalent orbit. The details are a little bit complicated if the binaries are eccentric or not, but roughly this periodic light curve has the same period as the supermassive black hole binary. So that's interesting. It's also interesting that knowing the sky location and the gravitational wave frequency can improve our strain measurements by an order of magnitude. So if we know which galaxy to look at, and if we know roughly what the gravitational wave frequency should be by this periodic light curve that might be coming out of the AGN, or active galactic nucleus, then we can do 10 times better in our strain measurements. And that's certainly a way of trying to get to detecting continuous gravitational waves faster. And yesterday, Friday, I'm confused between time zones, the last working day that there was an archive new submission, my student, again, Andrew Casey Clyde, submitted a paper that showed that supermassive black hole binaries are 7 times more likely to be hosted in quasars than in a random galaxy. And so in the future, I think that doing targeted searches for quasars to be the hosts of supermassive black hole binaries could be much more fruitful than just doing all sky searches and getting huge, 40 square degree large error boxes on the sky. That's in the best case scenario where we find something, right? But by doing targeted searches, again, we can do an order of magnitude better. And so from our current estimates, we think that there can be at least 2 supermassive black hole binaries that are detected by the end of the decade. And those are also interesting because they can induce anisotropy in the gravitational wave background, which is where my heart is. I love anisotropy. It was one of the first projects that I worked on when I moved from LIGO to pulsar timing arrays. And it's just so cool because you can import all of these data analysis techniques from the cosmic microwave background to gravitational wave backgrounds to start to make maps of the gravitational wave sky. And so these individual sources may or may not induce detectable levels of anisotropy, but that's definitely where the future is going to take us. So here I have some figures from a paper from 2017 where I simulated what the local nanohertz landscape would look like if we're assuming that supermassive black hole binaries are sourcing it. And there's a screening allowed supermassive black hole binary here. And then I said, okay, well, what would that look like if it were a gravitational wave background? And then what's the angular power spectrum of that gravitational wave background? So just decomposing the sky on a basis of spherical harmonics like you would do for the CMB. So this blue line here is a bit of a red herring. Anyone who's used heel picks knows that the smoothing has this, Gaussian tail to it. So if you turn off the smoothing, then this is just something like 80% of the background is swamped by this continuous wave source. But then you can say, well, this is a rare situation, right? So what if I just remove it? What does the map look like? Then it looks like this, which is starting to look much more like a CMB map. And then what I found is that it's about 20% of the monopole. So the anisotropy or the power and all of these higher order multiple moments is about 20% of the monopole. So that's also exciting. All right, so we've just found evidence of a gravitational wave background, and that is almost as exciting as Ariel's pulsar dance. Almost, not quite. That was very exciting. And it's not only Nanograv that has this signal in their data, but also the European pulsar timing array, the Chinese pulsar timing array, and the Parkes pulsar timing array with different levels of evidence. So what's next is going to be likely the detection of these individual supermassive black hole binary systems, and those will induce anisotropy in the gravitational wave background. And then hopefully after we find the anisotropy, LISA will fly. So we're going to be really busy. So when people ask what's next for pulsar timing arrays, the answer is everything. So thank you all for your attention. And for Ariel, please. I think we deserved louder applause than that.
This was great. Yeah, I'm my life as a pulsar. That's my next.
It's a very long life.
Yes. Questions, Nikhil?
Really nice talk. I've got a question about given the current constraints on the pulsar timing background and what we know from galaxy dispersion measurements and things like this, is there any constraint you can place on the mass spin of the supermassive black hole merger rate? So is it does it peak at 10 to the 8 or 10 to the 7 or something like that?
So the volume of the gravitational wave background we can constrain to redshift 2.5. In terms of rates, it's a little bit tricky because these are all very long in spirals, right? And so in this very lowest frequency bin, we have 10 to the 6 slowly evolving supermassive black hole binaries. And what we see in the detector is all in spiral. The mergers happen, so you're an expert, I'll directly answer your question. So the ISCO frequency of a 2 × 10 to the 9 solar mass binary is about 10 to the -6 hertz, which is right in between LISA and pulsar timing arrays. So right now there's no way of actually finding the chirp of one of the supermassive black hole binary systems. I've got some ideas on how we could do it, but right now this is very much an open question. So in terms of rates, I can tell you that in a Hubble time there's 10 to the 6 at 2 nanohertz, but it's also kind of difficult to ask that question here, right? Because you have such a long time scale. Each one is spending tens of millions of years in the frequency band.
Cool, thank you.
Yeah.
Yeah, I was wondering what is the reason for which you said for individual binaries it's more likely by factor 7 that they are quasar?
Yes, so if you, very good. I think that this is in my bonus slides. Yes, good. So this is hard for my neck. So you can take the gravitational wave background and then say, if I have, this amplitude of the gravitational wave background and I have a model of the gravitational wave background that's just created by a galaxy stellar mass function, so just any kind of galaxy, right? I find that there's a certain number of supermassive black hole binaries. And then if I say the same thing for quasars and then say, well, what if I say the quasar population is tracing the supermassive black hole binary population. It doesn't mean that it's powering the quasar. It's just saying we know that quasars are formed by mergers. This is another can of worms. But if you believe that quasars are formed by mergers, then maybe there's binaries in there, just like there might be binaries in an elliptical galaxy. And so if you compare the number of binaries that you would get in terms of quasar mass functions versus these galaxy stellar mass functions, there's 7 times more of them that would be in quasars. Yeah, so this is a kind of logical flow chart that tells you exactly how we calculate it. But basically this fraction is 7 of having more supermassive black hole binaries that would be found in quasars rather than in random galaxies.
Questions? Well, I have one. Let's see. So you've been, you know, I understand that there are less orthodox explanations in addition to supermassive black holes. There are other things that could be causing. You care to comment about those?
Sure. So there's a new physics paper. I don't think that I have the slide here. No. So in our new physics paper, it's more like it's 80 pages of all sorts of new physics. We go through different sources of the gravitational wave background that are not supermassive black holes. And there's a lot of cosmic strings models, as you could, guess. But actually, cosmic superstrings plus supermassive black hole binaries has a base factor of 100 to 1 over just supermassive black hole binaries. And so that's really interesting. We're still trying to figure out what that means, as in, is that evidence for cosmic superstrings? Some people say yes, some people say no. It's unclear. So right now what we're trying to do is figure out if this amplitude of the background that we're measuring is finally the real amplitude. So those of you who've been following the field more carefully might remember that the Nanograv 11-year data set had an upper limit of 1.45 times 10 to the minus 15. And the evidence for the background is at 2.5 times 10 to the minus 15. So then you would be very correct to ask, didn't you already rule that out? What happened? And what happened was pulsar noise. So we didn't correctly model the pulsar noise. And in fact, what we found was that we'd been eating away at the gravitational wave background signal, thinking it was red noise in the pulsars rather than the actual signal that we were looking for. So we kind of we kept digging away until we couldn't avoid it anymore. And then we're left with, when we had the Hellings and Downs curve, we were really sure that that red noise was the gravitational wave background. But then I'm so worried about us doing that again that now I have a student, Bjorn Larsen, and his paper was just accepted, who spends all of his time modeling pulsar noise. And in fact, what you can see, the really interesting one is 1713. This is one of, we call it like a heavy hitter pulsar. It's like a monster pulsar. It has a really long time span. It has over 10,000 timing residuals in it. This is a pulsar that really dominates the background. So without a custom noise model for this particular pulsar, meaning that you take extra care in your models for anything from the solar wind, right? Because if you had a big, coronal mass ejection like what we just had, you have a much larger integrated electron density between you and the pulsar. And that could, give you some red noise. And so here what we showed is that without these noise models, you have this pink curve, which is the, I think that's the pulsars, DMX, which is our previous model. And then the green one, which is a slightly more advanced model, but is really the same. But with our custom noise model, you get something that's much more consistent with our measurement of the gravitational wave background. So here, what this is telling us is that this pulsar is so noisy that it can't really help us measure the gravitational wave background, even though it's really, really heavy. It means that this noise that we now know is all of this red noise was being mismodeled as something else, right? And that this was like really a poor measurement. You can see that the amplitude and spectral index, I should say for supermassive black holes, the spectral index is 4.33. So it's about, I think Samaya was much better at this than I am. 4.33 is like here, right? And so this actually gives us much larger air ellipses, but at the same time is much more realistic. Mm-hmm. So I'm very worried about, these custom noise models and now trying to correctly model them so that we are not in a situation where we're eating away at the gravitational wave signal again, but that we're properly modeling it. So one of the things that I'm worried about with this preference for cosmic strings is that we're basically at the inverse problem. Now we're so worried about mismodeling the background, that we're leaving in too much noise, right? So I think that finally things will start to settle down between 1 and 2 times 10 to the minus 15.
Great, thanks. Any more questions? Doesn't look that way, so let's thank Chiara again. Great. Welcome back, everyone. The next talk will be given by Sheila Rowan, University of Glasgow, who unfortunately could not be here with us personally, but we're very happy she could still share with us what's to be expected for next generation gravitational wave observatories through this digital link. So, Sheila, please take it away.
Thank you very much. Apologies again for not being able to be with you in person. I'm going to give you an overview of what is happening around the globe at the moment in terms of next generation gravitational wave observatories, or long baseline interferometer observatories. I'm talking to you today, but of course I'm going to talk about the work of a considerable number of people, particularly in the Einstein Telescope collaboration and in the Cosmic Explorer Consortium. So I have no doubt that you will have heard this morning about the wonderful science that's being done with essentially the advanced generation of gravitational wave observatories. So of course, the Advanced LIGO instrument started in 2015 in the US. Q600, again, a smaller instrument, but using advanced technologies running since 2011. Virgo, which joined the Advanced Virgo, which joined the Advanced Network in operation in 2016. Kagra in Japan, having joined in 2018, contributing, and we very much look forward to a further addition to the Advanced Network in India, another version of the Advanced LIGO instruments in India in the future. And there is, of course, good, strong scientific motivation for why we have a network of detectors and not a single detector. So you've heard, I suspect, quite a bit about the current capabilities of the advanced network. And I think there is no doubt we can say it's been a monumental success, with a whole range of different science being delivered. Of course, the first detections being binary black holes, the science that comes with that. But this is just a reminder before we look to the future of the remarkable science that's been delivered with the generation of instruments that we have so far, both on their own and working in concert with electromagnetic instruments. I won't say too much more about that because I'm sure you've heard about that this morning. But what is worth reflecting on, I think, is that all that fabulous science actually comes from a generation of instruments that, in fact, are only probing, in some ways, the local universe. So on this plot here, you see on the right-hand side the distance out to, different things that we're able to probe, again with advanced second-generation so-called gravitational wave detectors, the portion of the universe really that we're probing. And there is so much more to see, to detect, so that the science motivation for improving the sensitivity of the instruments is considerable. And so targeting, again, the science with a future set of observatories is something where we want to make a step change. There are many things that we can and we do to upgrade the sensitivity of the advanced network. That's an ongoing process. There are things that we can do there within the infrastructures of the existing observatories. However, to make a step change, a transformational change, there is a vision on how we can do that, moving to new infrastructures, new observatories. So for that step change in capability, there's sort of two consortia, two sort of different groupings, again with some overlap in membership, looking at different future observatory infrastructure to give us that step change. On the left, you see an artist's impression of a future observatory concept, Cosmic Explorer, in the US. And on the right, again, artist's impression of a different observatory concept, the Einstein telescope, which would be in Europe. And so I'll talk a bit about the timeline for those, where we are with those, bit of a future look, and of course, a little bit of the science, again, that we want to do with those. So I think the first thing to be aware of is that, you know, as probably everybody in the room knows, this is not a field in which things happen instantaneously. Already, you know, thinking about the next generation of observatories is something that we've been doing for a couple of decades now. In terms of the Einstein telescope, there was actually a workshop back in 2005, an exploratory workshop, to look at what was then called 3G, third generation gravitational wave observatories, to look at a bit of and out of that came the idea to have a design study for such a thing. So this is way back before any gravitational waves had been observed. We were already looking to the future. So that was funded in Europe. There was an FP7 award involving a number of countries, France, Germany, Italy, the Netherlands, and the UK. Later extended to include more countries. It's very much a pan-European proposal. And you can see the cover there of conceptual design at that point, already larger than the current observatories, moving from a few kilometres to 10 kilometres. Here, the vision being to put the instrument underground. Of course, you can see that time has moved on since then. The conceptual design study for the Einstein telescope was published back in 2011. You can see the cover there with a bit of a history on it as to how things moved forward, supported by a succession of both European and national awards to look at some of the technology, some of the design work. But there really, of course, came a step change with the detection of gravitational waves, which has given considerable momentum to, you know, the need to think about the future now that we understand what the advanced detectors really can deliver and what a future observatory might do. So there was an update to that design, which was done in 2020. Because we have learned such a lot, again, from operating the advanced generation of instruments, it's allowed that to feed in and shape the future concepts. And indeed, the Einstein telescope as a future large scientific infrastructure was accepted onto the S3 roadmap in 2021, when the roadmap was opened to proposals for new infrastructures. Supported with Belgium, Spain, and Poland. There are other European countries also, you can see, who are also lending their weight to that. There is a formal organisation, again a consortium, an organisational structure on the whole led by INFN and NICHEF, but that was a big step to enter the S3 roadmap. So a little bit more then about what we're looking for in a future observatory and how we might conceptually see that delivered. The thing is to widen the frequency range over which we have sensitivity, so a wider range than we have currently with the advanced network. One piece of science, again, that has come out of our studies with the advanced network is the existence of massive black holes, looking at the intermediate mass black hole range, encouraging us to improve the low frequency sensitivity of whatever observatories we build next. We certainly understand now the desire for localization capability and the need to be able to localize, work with our colleagues with electromagnetic and other observatories. We'd like as much sky coverage as possible. polarization disentanglement, if you can get it. High signal-to-noise ratio, I'll come back actually specifically to that question and what we might be able to achieve a bit later. So in thinking about what's desirable, those translated in ET to a set of design choices. You saw the conceptual design that showed an interferometer underground. Thinking about the low frequency sensitivity there, if you put an instrument underground, you potentially reduce the gravity gradient noise that might affect the instrument, which is one of the considerable challenges to achieving low frequency sensitivity. If you can go to low temperatures, that means you can tackle another source, a critical source of noise in our instruments, the Brownian thermal noise of the mirrors and the test masses themselves. It's a multi-detector design in the first instance, actually 6 interferometers you can see there, 3 that would be cryogenic, 3 at room temperature. Cryogenic ones, you have to use different technology than the advanced instruments, change wavelength, silicon optics so that you can cool that down. And one of the key things we can do is make the observatories larger, longer arms, in the case of the Einstein telescope, 10 kilometers. So that's the sort of design concept that has come through from that 2005 workshop 2020 into the S3 roadmap. Of course, we want to evaluate that and make sure that the design is has had everything taken into account to the best of our ability. So actually, of course, that's slightly a different design than the current LIGO, advanced LIGO, or advanced Virgo instruments, which have the L shape. So there's been a bit of work taking into account the things that we have learned from the current observations, how the science case has developed in light of that, what we know about operating detectors, the broader international picture, which I'll talk about more in a bit, because as you can see, from our first our advanced set of detectors, the current detectors, the ability for network working is an important factor. So that international picture, that is still the case for next generation observatories, how any network of instruments might be able to deliver science. There's the fact that we need sites for these instruments that are currently for the Einstein telescope, and I'll say a bit more about this in a second. 2 candidate sites with strong support in Europe, potentially a 3rd site. So the Einstein telescope collaboration is working currently on analysing the configurations, triangular, L-shaped, trying to consider what options might optimise science return. So I'll just highlight a particular paper from last year, doing some of that work, looking, again, if you take 2 15-kilometre L-shaped instruments of particular orientation, how that might compare with a triangle. Improve science return on some science targets. Of course, it's not always that simple, but it's an active area, I would say, of discussion. What's the right configuration to look at going forward? What would optimise what we can deliver? I mentioned there were 2 candidate sites that have officially positioned themselves as being interested in hosting the Einstein telescope. One of those is in the EMR, Euro-Meuse-Rhine region, if I've got that correct, between the Netherlands, Belgium, and Germany. So you can see on the map there is a region where the borders of those 3 countries meet. There's another site in Sardinia, again, which has undergone a fair amount of investigation as a potential site. There have been discussions around another potential site in Germany. I think they have not officially launched themselves as a potential host. As you might guess, choosing where to place such an observatory has to take into account a large number of factors. Some of those scientific, geophysical properties of the particular site, the ability to have the services and infrastructure needed to host such a large, and I'll talk about scale again in a little bit. So some of that work again has been ongoing over the past few years. First of all, for the EMR site, there was a substantial funding bid for, and indeed, in fact, awarded in the Netherlands as part of a larger piece of work there on national growth funds. Again, it was considered on that basis, with several tens of million euro for geological studies, looking at some of the R&D, the technical R&D, looking at putting in place organisation, as well as discussions around a potential contribution on a much larger scale, should that be the site chosen from the Netherlands. Parallel activities, as you might imagine, in Italy. This is another project, the Einstein Telescope Infrastructure Consortium, again with tens of millions awarded, this time from the Italian ministry under their National Recovery and Resilience Plan. So this is utilising the sort of benefits that can come from hosting these large infrastructures to motivate these studies. So there are a number of groups in Italy again involved there, helping evaluate both the site and develop the sort of ancillary R&D and technical developments needed. And these are, I should say, not the only two pieces of work that are contributing here. There are other institutions, other European national projects contributing to different parts of the Einstein telescope. But it gives you a bit of flavour of the level of interest and the sort of magnitude of support that's going towards driving the momentum for a next generation infrastructure in Europe for gravitational waves. And it is substantial. Here's some rather nice artists' impressions of what the underground infrastructure might look like. Again, very, very large scale infrastructure, and you can see we care about the scientific part, but there are a whole other set of drivers as to hosting such a thing. On the other hand, in the US, again, the vision there is under the heading Cosmic Explorer. So that's the US concept for a next generation observatory. It's different in its initial design concept. I'll talk about that a little bit. So in the US, the vision would be for two L-shaped observatories, this time on the surface, not ground, one 40 kilometres and one 20 kilometres. This time not, at least in their first instance, cryogenic. They would use the same sort of fused silica type technology for the mirrors, 1064 nanometer lasers. So that's an evolution of the type of technology used for advanced LIGO and advanced Virgo. Both Cosmic Explorer and ET target sort of an approximate 10 times increase in sensitivity over today's observatory. So the broad aspirations for sensitivity improvement are similar. They differ slightly in their detail in terms of design curves. And as we talked about earlier, in both cases, we're thinking about this in terms of a global network. Cosmic Explorer thus would be part of a network that might see ET there, and also on the same time scale, LISA as a space-based, and so the science has to be thought of in that context. So we talked again about the sort of national and multi-country involvement in ET. Cosmic Explorer is envisaged as a National Foundation-led project. There are currently several coordinated awards issued by the NSF working on different aspects of the Cosmic Explorer conceptual design. You'll see a few of them there. And again, I'll talk a little bit about site evaluation in a moment. There is also international involvement. The UK currently has an award that allows us to participate in both Cosmic Explorer and ET, again working on aspect of the design. Other countries, other international countries are also involved. The NSF processes, again, define the path for large infrastructures. We are currently in the conceptual design phase, again, for Cosmic Explorer. Talked about the S-Freak map in Europe. In the US, of course, the Astro 2020 decadal survey that was the relevant roadmap, sort of anchored evaluation of the potential of a next generation gravitational wave observatory, and that was very strong in terms of its endorsement, central to achieving the science vision laid out in the survey's roadmap. So there's a sort of, again, a parallel path there. To take that forward then, in the US, the National Science Foundation, the Maths and Physical Sciences Advisory Committee, set up a subcommittee specifically to look at a set of concepts for a next generation observatory in the US and make a recommendation on it to the NSF. You'll see these timelines start to look familiar, again, going from now through to the mid-2030s. That has recently reported. It's a public document. I believe you should be able to take a look at that. And this committee took input from the community, looked at a set of white papers, considered the global picture, again, took into account the fact that the Einstein telescope, again, has its own momentum in Europe. We talked about the future of potential LIGO India detector. And it made some recommendations. It made recommendations that in a future with ET in Europe, that the US should focus on a cosmic explorer-like concept, 40-kilometre instrument. Without ET, should ET for any reason not go ahead, the committee foresaw the need to have two instruments in the US, 40-kilometre and the 20-kilometre, that initial design concept that we looked at for Cosmic Explorer. It also made some quite specific recommendations about the advanced detectors in the era of next generation instruments, that advanced LIGO facilities would be phased out by the time Cosmic Explorer wideband sensitivity of one or two detectors is better than advanced LIGO. I think that clearly makes sense. It also recognised that in a network, having that LIGO India instrument, again, where it's geographically separated, was important for multi-messenger astronomy. So it was, again, made some very helpful recommendations there. Talked a bit about sites in Europe, sites in the US. That's another piece of work that's ongoing. Again, as I mentioned, one of the NSF awards supports that work. There have been preliminary studies that suggest there are a number of potentially promising sites. It's still non-trivial to find, suitable sites that could host things, because now we're talking about instruments with 40-kilometre long arms. So those sites are now under further study, and it's in the US a different piece of work that needs done, again, for different sort of reasons. Some of the geographical and geophysical questions are the same, but there are sort of particular issues associated with choosing scientific sites for large infrastructures in the US. And that's, if you look at a map of the US, there is no land that does not have a set of indigenous people who've been associated with that land. And work in that space, understanding how to, appropriately work with local communities in choosing a site and potentially constructing a site is a specific piece of work. Again, that's part of the US activity in this area. So that's kind of the big picture on what's happening technically. Again, what the sort of momentum is, the paths are towards a next generation instrument with some sensitivity aspirations. Of course, that's to deliver science. To just give a couple of examples of the sorts of things that could be delivered with a third generation, a next generation rather, observatory. On this sort of graphic here, this is one where we're in the middle of the plot. You can, and looking outwards in terms of volume of the universe, you can see the sort of 150914, and that would be our first detection of binary black holes marked, and its distance out 170817, binary neutron star with its equivalent electromagnetic signals. And then marked in the concentric circle are the range and capabilities of different generations of gravitational wave observatories for binary neutron stars or for stellar mass binary black holes. And by the time you get to the sensitivity that could be achieved with next generation instruments, you can see for binary neutron stars or for stellar mass black holes, we basically would be able to detect them all. And that's why this is a remarkable step change. Mentioned improved signal to noise ratio. This is a slide again from Satya Prakash, my colleague at Penn State, many of you will know, showing the improvement in signal to noise ratio that one could expect with the different generations of instruments. Taking as examples in the middle there, again, that the signal to noise ratio of that first detection of binary black holes. So in the first observing run advanced LIGO, signal to noise ratio of 25. Once you get to ET and Cosmic Explorer, it's 800, it's 2100. So these exact numbers, I should say, they'll vary a bit. The difference between ET and Cosmic Explorer, that depends on exactly what design choices are made. So I wouldn't worry about the exact number or the detail and the difference. Those are design choices to be made. But what's striking are the numbers. It's signal to noise ratios of hundreds and of thousands. And so the science that you can do, the precision measurements that this enables, give a quite different capability that we will have in future. Of course, those examples are just part of a whole suite of science case. There are papers and papers written on this, so I will not go through it all, and there'll be others here today who will talk eloquently about the science that can be delivered. But it is a step change. It is extraordinary, and it is I think, a compelling driver for what we want to do. Inside those large infrastructures, of course, are upgrades, evolutions, new technical challenges that we have to address. We've talked about longer arms, 10 kilometres or up to 40 kilometres. That actually brings with it technical challenges just to be able to deal with arm lengths that large. ET, potentially underground, Cosmic Explorer perhaps not. Again, that brings its own challenges. Perhaps higher laser powers and multi-megawatts. So there's work on laser development, how to handle those higher powers, significantly larger, heavier optics, not tens of kilograms, hundreds of kilograms and up, but our mirror substrates, possibly at cryogenic temperatures, a switch in material, new laser wavelengths, lower thermal noise coatings. So the technical challenges, and they are in some cases different, but actually with overlaps between the two projects that we've talked about, between ET and Cosmic Explorer. Although their design concepts in some ways are different, there are certainly a whole range of technical challenges that are common. And so, the global field is working together on those, identifying those, and working together on ways to tackle those. Since one of the lessons learned that we have is that, again, both the science that we want to deliver benefits from multiple instruments, but the technical challenges, again, we really need to work together on. So having talked about what's happening currently, there are certainly opportunities. You can see funding is starting to flow in terms of addressing these issues, both on the conceptual hardware design, but also, and I haven't talked much about this today, there are, of course, data analysis, computational challenges, hardware challenges. This is a completely different regime in terms of the analysis that needs done. So there's considerable work that needs done there. Again, that's common between the consortia. It needs new design approaches. The consortia welcome new members. I've put up the links for the two consortia there, and there are information there about how to participate and how to join if you're not members of the consortia already and would like to be. I'll mention one last thing, which is, of course, even this next generation are just part of the story. of the different ways in which we can detect and study gravitational waves across the frequency spectrum. So I mentioned LISA earlier, just to flag mission adoption has been achieved this year. It has this potential launch date in the mid-2030s that puts it alongside the next generation ground-based instruments. So it's a fantastic potential suite of things to come. So just to finish, as I said, no matter the fantastic science we have at the moment, it's only a small fraction of the gravitational waveverse. We have a good vision for the future. There are technical challenges. Planning is underway, and more folks in the field would be most welcome. Thank you very much.
Thank you very much, Sheila. We have time for questions.
So, can I be heard? Can she hear me? Can you hear me?
Yeah, I can hear you.
Okay, this is amazing.
Yes.
So in this no black hole left behind plot you have, we've seen it a few times today. So I have a burning question that I've always wanted to know. The comparison between Cosmic Explorer and Einstein Telescope, it looks like there's a little sensitivity flip between the black hole binaries and the neutron star mergers. Is there, like, one is more sensitive to one and one is more sensitive to the other? Is that just because of the frequency range that it's sensitive to, or is there some other fundamental way to understand that?
So I don't think there's anything more fundamental than that. We'll have different frequency. The exact design curves for ET and CE are slightly different, and it depends on exactly the choices you make in terms of your hardware design, exactly what the frequency sort of limits of the noise looks like, and then that changes your sensitivity to different sources. And actually, there's a bit of work. It's part of the funded work at the moment to essentially do exactly that, do the trade study of tying the science that you deliver to the choices you make about the exact sensitivity curve and design.
Okay, so there still could be some changes then in how that lands, I guess. Yeah, okay, thank you.
Another question. Well, people are thinking I have one. So you mentioned this amazing improvement in sensitivity compared to current instruments. I'm not sure if you mentioned this, and if you did, I apologize. What about the localization you expect from these different combinations you described?
So I don't have exact numbers to hand. I'm not sure I could give you a quantitative answer on that, but it certainly has been looked at, and it's part of all those studies in terms of particularly choosing the number and location of different instruments in future. But I'm afraid I don't have a number at hand in terms of localization.
All right, no worries. Let's see, another question. I think it was pretty clear. There are no further questions. So thanks again, Sheila, for being with us remotely. And yes, let's give her a round of applause.
My pleasure. Thank you.
Great. So next up, we have 3 shorter talks. First one out is Carl. Please. Carl Haster from Nevada. University of Nevada. There you go.
So, thank you again to the organizers for putting on this very nice symposium and for the Academy for hosting us. So I wanted to expand a bit on some part of the physics that have been mentioned already. And this is what we can say about the astrophysical population of black holes that we have now, over the last couple of years, been fortunate in observing with our gravitational wave detectors. So this figure here has already been shown a couple of times, with the vertical axis showing the masses that we claim to have seen. This, it's a very impressive looking figure, but it doesn't tell us the whole story. And it doesn't tell us the whole story in a couple of different ways. So to start with, we are not yet at a stage where we can say with certainty exactly what the masses we have, or what the masses of the black holes that we have observed are. There is some amount of uncertainty, partially due to the loudness and noise in our detectors, partially due to variation and correlations and so on in the models we're using. So in practice, we infer our binary parameters as potential distributions and the correlations therein. And as shown here is the first is the set of detections made during the first couple of years of our observations with LIGO and Virgo. Having seen this many individual observations, the natural step to take then is to consider them all as part of a broad population. So the population of black holes that we have observed so far during the first 3 observing runs of LIGO, Virgo, and Kygra can be represented in this figure here that Patrick showed this morning, I believe. So what this visualizes is the differential merger rate as a function of the primary mass or primary black hole mass of our population. And there are 4 different lines or 4 different models shown here. They all have their particularities and individual features, but you can see a broad theme going on with a decline following roughly a power law and a significant bump around 10 solar masses and another one at 30 solar masses. So in addition to just measuring the distribution of individual black holes or the primary mass of the black holes in our binary, we also infer we can also make a statement about the distribution of the mass ratios, or in other words, the mass of the secondary black hole. So in general, we prefer our binaries to have roughly an equal mass, but there's still support towards more unequal mass binaries. And I should say that the difference between the blue and the gray lines here is the difference of adding a couple of other, or another 20 or so binary black holes to the population that has been considered. One thing I should mention is that, so a piece of physics that is of particular interest to a couple of people in the room is the existence of a potential mass gap at the high mass end. So Patrick mentioned the mass gap between neutron stars and black holes between 3 and 5 solar masses. Depending on the specificity in supernovas and specifically the periinstability supernova, there could be a mass gap at around 50, 60 solar masses up to 100. In the population we have so far, we don't have any evidence specifically for a mass gap. There aren't that many black holes at those masses anyway, but if we try to look for a dearth of black holes, we don't find any strong evidence for that at this stage. We can also look if our merger rate evolves with redshift, and so far we have strong evidence for this to happen. So you can see here on the left a figure showing the merger rate as it evolves with redshift, and it appears to very nicely, for now at least, follow the star formation rate out to the redshift that we're sensitive to at the moment. And for now, we're only assuming this evolution to follow a simple power law, and so far that seems to be a good enough model. We can also make statements about the spin of the black holes, and the combination of the different spin parameters that we're the best at measuring is this effective spin that you can see described here on the left. And the population we have seen so far doesn't appear to be very strongly spinning as inferred by this single parameter. We can also make statements about the the amount of precession that our binaries exhibit. And again, there is no strong evidence for large precessions in this one population. So far, I've only talked about the population or different viewpoints of this population as individual concepts or as individual statements. So we can say something about the primary mass, we can say something else about the mass ratio, and we can say something else yet again about the constraints on the spins. From astrophysics, you can generally assume that every single piece of astrophysics is poking at every other single piece of astrophysics. So we can assume that there should be some amount of structure in this population. So in a couple of studies, to start with, led by Tom Callister here, we looked specifically if we could identify and characterize some of this structure. So what's shown here in this figure is an overlay of all the individual probability distributions of the mass ratio on the vertical axis and this effective spin parameter on the horizontal one. So far at this moment, we're not assuming any connection between any of these binaries. Everything is analyzed as their own special little observation. And this two-dimensional set of two-dimensional distributions are quite broad, but they're still kind of centered here around a chi-factor of 0. If we do the same type of population analyses that have been done in the past, so the one I've shown you before, we can reweight our individual event posteriors or individual event distributions with the information of them all belonging to the same population. And you can see that adding this extra population constraints tightens things up quite significantly. And again, you can see that the preference of a 0 chi-effective value seems to be even stronger. What we looked for at this stage, though, was to see if we allowed this population model to have some correlation. We know that from the description of the gravitational waves themselves, mass ratio and chi-effective have some degeneracies, so there could be some potential correlation caused by that. So we expanded our population model to allow for just a simple linear correlation between Q and chi-effective, or between mass ratio and the effective spin. And we found one, which was very exciting because there's another piece of evidence to try to connect to astrophysics. The complicated thing, though, was that there are astrophysical arguments for why there should be a correlation between these parameters. The standard explanations would suggest a correlation going the other direction. So having this positive correlation was a surprise in that sense. So in our initial study, we only looked at the first 47 or so binaries. And we tried our hardest to make this correlation disappear, and we were unsuccessful in doing so. And even when we add in the full 01, 03, 02, 03 set of binaries, the population or this correlation persists. In another study, we looked to see if we could find another one of these paired up correlations. And the most significant we found there was between, again, this effective spin parameter and the redshift evolution of the population at large. So what we found was that if we allow for some correlation, or again, a linear correlation between the effective spin parameter and redshift, the redshift distribution nicely broadens with increasing redshift. And again, astrophysically, there are a couple of different ways or a couple of different arguments you can make for why this is the case. Relatively easy one would be to say that there is some metallicity dependency in the stars that we see that eventually form black holes, and that could have some impact on the black hole spins and also their spin configurations. This could also be some evidence for the assumption of all of our binaries belonging to the one population kind of falling apart. So if you have competing subpopulations, that could be so if you construct your observations as a combination of individual subpopulations, that could be yet another way of explaining this variation with redshifts. So this is coming towards the end of my presentation. I wanted to show this set of figures from a nice study by Jack Hainsel, where they relaxed our fairly rigid assumption about a nice and well-behaved linear correlation, and specifically for this last model I showed you, where the effective spin population broadens with redshift. This is represented in this study by the standard deviation of the chi-effective distribution increasing with redshift. What they did very nicely here was to allow for a more generic functional dependency between the redshift and the effective spin. And what they find is that they no longer have a strong support for this broadening with redshift. So that constraint might be primarily coming from the large number, but still the binaries that we have seen at relatively modest redshifts so far. So I have mentioned in this talk only the black hole population. There should also, so we have made statements about the neutron star population. We have seen significantly fewer neutron stars than black holes. So those constraints are less robust for now. But in the future, we should be able to both make connections and connections between the black hole population and the neutron star population, and also see where and how they overlap with each other. And also, as we accumulate more observations, the constraints and inference we can put on the black hole spins should tighten up even further. And then I wanted to make a shameless plug for an upcoming study led by my postdoc in Vegas, Marios Kolomanopoulos, where we're going to make this correlation program as broad as possible so that we can correlate everything with everything instead of just limiting ourselves to this single pair and potentially linear correlations. So look out for that in the coming months. So we have many more observations coming in, where only a small part into O4b. The observations or the constraints or the population I have talked about today only considers the events shown here in black, so up to 700 and a few days worth of observations. Since then, there have been another 100 or so observations or events announced. And once we have finished our data taking and done some more careful studying of that data, a new and updated population will be presented, and then we'll see what we can find therein. Thank you.
Thank you, Carl. Questions? Okay.
This bump you pointed out at about 30 to 35 solar masses, do you consider that well established now? And if so, what's your favorite explanation for it?
So the existence of the bump is robust. With the different models that we try to make it go away, it doesn't go away. So that there is a bump there is fairly certain. I think, so it could have been explained by a pileup of black holes caused by the existence of parent stability supernova and pulsational parent stability supernova that would remove enough mass from the stars so that all the big stars would only be able to make black holes at around 30 solar masses. I think if that was the main explanation, then we would have liked to have seen more evidence of the actual parent stability mass gap. And given that we don't really have, or we don't have strong evidence for the existence of that mass gap, it remains to be seen.
More questions? Stephan?
Just comment on the physics, what that means for the parent stability supernovae?
So the parent stability supernovae is that you form electron-positron pairs inside the stars, and then you destroy, or the energy created in that annihilation, effectively, eventually, is enough to remove some of the mass from, or no. So the electron-positron pairs actually disrupt the stars entirely at that point. So you don't form a black hole from those supernovae.
So connected to that, you're saying you don't know if you do see or not, a parent stability gap. So what statistics? I mean, do you think with the statistics already in the can, you'll be able to say something more firmly, or you will take 0.5? What's your current thinking?
So I think with the other 100 or few hundred extra observation, we might get an 0.4. Hopefully the statistics for justifying the mass gap will improve. I should also say that there are other ways you can create black holes in that mass range without direct collapse from a star. So if we have multi-generation mergers, so you have two black holes, you smash them together, the remnants can, in principle, find another black hole and merge together in a time relevant for our observations. So there are other means of making black holes in that mass gap.
Yes.
When you're looking at this correlation of the chi-effective with redshift, how do you model out the effects of the correlation between redshift and signal-to-noise ratio and that sort of issue?
So in the population model, that's something I should have clarified. All the population constraints I show here represent the actual astrophysical population that should exist out in the universe. So all the selection effects, so all the signal-to-noise ratio dependencies, and all the parameter-specific observability criterion have already been accounted for in those in these constraints. So the things that are far away and not very loud contribute the appropriate amount of information. And similarly, the fact that we are less good at seeing low mass objects compared to high mass objects are also accounted for.
All right, I don't see any hands up there, so let's thank Carl again. Next out is Nikhil Sarin from Stockholm University. And we are back to the multi-messenger exciting story. Let's see. Hopefully. There you go.
Awesome.
Luckily not.
All right. I hope everyone can hear me clearly. And just to make sure everyone's awake, can people just stretch their hands or something? Thank you for the invitation, and I'm really excited about talking. I had to make this extremely long trek this morning all the way from Stockholm University to this beautiful place. I hadn't been here before. And I want to talk about mergers of neutron star binaries, but with a slightly different spin. I don't want to just focus on gravitational wave observations. I want to focus on what we can learn from the combination of gravitational wave observations and everything we know so far and potentially are learning from in the future in the multi-messenger era from electromagnetic observations. And so we already went through this obviously today. This is just a slide grab just showing sort of the different plots that really summarize this amazing event, GW170817, which was this incredible thing where we had the first gravitational wave signal. We saw the in-spiral, and then we lost it somewhere in the merger. And then 1.7 seconds later, we had this gamma ray burst that were observable with integral, Fermi, etc. And then, again, also my favorite plot, so Samaya already showed this in detail, but one of my favorite plots is this one, which is, this laser's not working anymore. Okay, I'm going to stop using the laser. But one of my favorite plots is this one, which is showing the evolution of the spectrum, so taken with VLT, which is, it was a bright blue source, and then with time it started decaying and then became redder and redder. And so you can take the spectrum, but then you can also take the photometry, and so the plot on the right top panel is showing the compilation of all the data that we had for 170817, the kilonova itself. And that was, beautifully compiled by Ashley Villar, and that's showing this fast transient that is, peaking and then decaying in a time scale of a week or so. And then, again, this plot at the bottom is basically this much longer time scale, potentially something that is still giving off electromagnetic radiation that is observable now. And that is essentially when this jet, this relativistic jet that produced the gamma ray emission, slams into the interstellar medium and produces a synchrotron emission. So I want to take a slightly different look at, GW170817 and other binary neutron star mergers in general, and really focus on what happens in the broad sort of spectrum of these things. So in panel A, I've got, 2 neutron stars. They're going around in spiraling, emission of gravitational waves brings them closer and closer together. And then in panel B, they merge. And then immediately, there's sort of different pathways you can take, and these pathways depend on what the mass of the binary is. So, if gravitational wave detectors are operating, they'll tell you what the mass of the binary is. And then also something known as the Tolman-Oppenheimer-Volkoff mass, which is basically the non-rotating maximum mass of a neutron star. And so we don't know this number, but if we did know it, and if the binary was above sort of 1.5 times MTOV, then what you expect is that binary neutron star merger will, within less than 100 milliseconds or so, promptly form a black hole. So that is shown in this sort of A, B, and C. If you're below sort of 1.5 times MTOV, then even though you're above sort of, the Tolman-Oppenheimer-Volkoff limit, you can still survive for some amount of time, and this is referred to as a hypermassive neutron star. And this neutron star is basically, really hot, so Stephan talked about the temperatures, and these are 10 to the 12 Kelvin or so, but it's also differentially rotating. And so these thermal gradients and differential rotation means that you can survive for about a second or so. And so this neutron star in panel D, this hypermassive neutron star, is going to survive for a second or so and then collapse into a black hole on that delayed 1 second time scale. That's all well and good. If this neutron star mass, the remnant, was even lower than that, if it was about 1.2 times that MTOV number, which again, to emphasize, we don't know, then you can actually survive for an even longer amount of time, and that time scale could be as long as 10 to the 4, 10 to the 5 seconds or so. And if in the circumstance that you are where the mass of the binary was, some number which was less than MTOV, this unknown mass, then you would end up in a situation where you formed an infinitely stable neutron star from this gravitational wave from this merger. Now, the key point I want to stress is that gravitational wave observations, let's try this again. No.
Yeah, it works. Yes.
But it's moving really weirdly. So this gravitational wave observations really stop here. Current observations have no way of telling what happens all the way up here. We can only really detect, the last few cycles and the merger, a little bit of the merger, but we can't tell if this is a prompt collapse into a black hole or what happens in the post-merger phase. But all the electromagnetic emission that happens is very sensitive to what happens in this phase.
every electromagnetic signature you can think about is very strongly influenced by what pathway you took. And so while you might know the masses, if you don't know what happens here, then you have trouble understanding every single detail about what is going on in the system. And so really the problem comes down to this sort of schematic where you have this central engine, which is in this case a black hole, but it doesn't necessarily have to be. And you have all this electromagnetic emission that is coming around from this object. So you have the kilonova, which is essentially, you know, thermal transient from our process nucleosynthesis. And so there's ejecta that is launched during the process of the merger. It might have different mechanisms. It might have different electron fractions, so it looks different colors. But then this central engine launches a relativistic jet. The jet interacts with that ejecta. It actually eats up the ejecta itself. That also produces some sort of emission. And then when that jet reaches some sort of radius, it produces gamma ray emission, which was the 1.74 seconds later, what we saw in 1708-17. And then, you know, when that jet slams into the interstellar medium, it produces the afterglow, which is the emission that we're still seeing 1,000 days later from 1708-17. But the problem is that all of this emission, sorry, I should be pointing here, all of this emission is really coming about from what this object is doing, but we can't really see it. You know, we have to try and infer what's going on at the heart of the system from these messy sort of physics observations. Unlike gravitational waves, these observations, these models are really messy. And so this is something that I spent a lot of time working on. And one of the questions you can ask is, well, we had amazing observations for 1708-17. What happened with 1708-17? And so the answer is not clear. So 1708-17, we had amazing observations, the gravitational wave observations and the electromagnetic observations. And so some people argue that 1708-17 went through this prompt collapse channel, where essentially the black hole was formed basically instantly, within a second. Some other people argue that no, that's not true. It collapsed within 10 seconds, so 1 to 10 seconds, and it must have formed a hypermassive neutron star first. Some other people argue that no, it actually should have actually produced a supermassive neutron star that survived for 3,000 seconds. And then all of that means that you can constrain the mass of the neutron star, the Tolman-Oppenheimer-Volkow limit, and this is somehow the best constraint on the TOV mass we have, and it's the upper limit of 2.3. And that's purely because we know the gravitational wave mass from the 1708-17's gravitational wave observation. And we know that it must not have made a neutron star that it's infinitely stable. So just on those two facts, we can work out that, okay, this number should be at least 2.3 and lower than that. But beyond that, when did this system actually collapse? We don't know. And so really, you know, another thing that I'd like to spend a lot of time thinking about is, well, 1708-17, and I don't need to stress this to this audience, especially after the day of talks we've had today, you know, was a historical observation. It was, you know, an incredible event. It's an event that I think most of us are going to remember in our lifetime. But it's not the only observation of our systems in our galaxy. So there's, you know, neutron star systems in our galaxy. There's short GRBs. There's other neutron star systems that we, you know, other mergers involving at least one neutron star. And if you want to figure out, you know, this phase diagram of the universe that Stephan showed, or where these elements are produced, it's worth looking at what all the observations are telling us. Not just, you know, keep looking for observations like 1708-17, where you wait and get another binary neutron star merger in coincidence with a gravitational, with a gamma ray burst or electromagnetic counterpart. And so with that in mind, another thing that really, you know, why haven't we done that already? And because I spent a lot of time in New Zealand, one of the things I love doing is sort of forcing relationships with Lord of the Rings. And so the unknown that rules them all is this thing known as the binary neutron star mass distribution. So if we don't know what are the masses of the binary neutron stars that go on to merge, then we can't really know what everything else is going on. And so this plot is just showing in histograms, for example, just the binary neutron star systems in our galaxy we see in radio, in blue. And in red, it's all the other neutron star systems that exist in white dwarf boundaries. So you can do a fit with, so in total there's about 70 systems on this plot here, and you can do a fit and you can see that, all right, the binary neutron star population is well described by a single Gaussian, really well described. And the population of total neutron stars is well described by a combination of two Gaussians. We love Gaussians, and especially in fitting, because there's reasons for that. So that's all well and good. When 1708-17 happened, we were really happy. Because on the right-hand side, it's essentially the same plot, but instead of the neutron star mass, it's got the chirp mass of the binary itself. So when 1708-17 happened, if you draw a histogram again, and you draw a vertical line for 1708-17, and that vertical line really represents a bigger uncertainty on the chirp mass than we actually got from the observations. And 1708-17 lies right in the middle of binary neutron stars in our galaxy. We're really happy. Awesome. Then 1904-25 happened, and that's a 5 sigma outlier from the galactic double neutron star system distribution. What's going on? Why doesn't it show up in the radio population in our galaxy? Immediately, there was a whole series of papers, and so if you're especially familiar with stellar evolution, there's always knobs you can turn. And so one of the ways we thought about explaining this binary was that it's actually a system which is fast merging. And how is it fast merging? That basically somewhere along the evolution of this two neutron stars, one of the helium envelopes expanded, one of the helium stars expanded, and basically there was a mass transfer episode, a common envelope, which brought the binary really close together. And so the binary essentially merged within 10 million years. And that's why it doesn't show up in radio. And so you can do this sort of study, and you can actually go on and fit the double neutron star systems we should see, in radio, and double neutron star systems we should see in gravitational waves. And this was done by Shanika in Australia. And you can sort of reconstruct what the birth distribution of neutron star systems is, and what you should see in radio, and then what you should see in gravitational waves. And so this is really nice. All right, maybe this is the way. This all seems really good. But then if you look at short gamma ray bursts in a way tell you about the delay time between a merger and when it was formed. Because short gamma ray bursts, we observe them, the localization of the short gamma ray burst tells you how far away from the galactic sort of center the merger happened. You don't really see any evidence for a short merger time in the short gamma ray burst population. So this is a problem. So now, I think if you'd asked me to give this talk maybe about 6 months ago, I would say that we're still in this a little bit of a crisis where we don't know exactly how the system formed. But something happened which, helped us. And so there was this amazing discovery which was published in Science recently, which was a pulsar, which is in orbit with a compact object that is between sort of 2.1 to 2.7 solar masses. So this nature of this object is not clear because it's in this mass range. It's not a pulsar, we know that very well through very good deep limits. And so we also don't know the mass exactly because the orbital inclination of the system is unknown. But really it's in this range where it could be a very heavy neutron star or it could be a very light black hole. And now that's very interesting because if it's a very heavy neutron star, it's much more like 1904-25 than any other system, and it is something that is observable in radio, at least one of the components is. Or it's a very heavy, or it's a very light black hole, in which case it's much more like GW23 or 529. So now we're starting to sort of fill out this parameter space, which we previously thought could not form in our galaxy, and we were saying, oh, maybe it's metallicity, or maybe it's something else. Maybe it was just selection effects. And so that's really interesting, and one of the ways you could actually form this binary is through an exchange encounter. And so when this binary actually merges at the end of the universe, it's actually spent some time and did that calculation. If you believe the eccentricity measurement, this will merge literally about 10% of the way away from the Hubble time of the universe. So if you're around, we'll see that. But this is a millisecond pulsar system merging with a heavy object. The electromagnetic emission is going to be very different from 1708-17. And Stephan already did the simulations of what this might look like, at least with a sort of spinning consideration. And so he has the plots for you to show. So then focusing again on the jet instead. So we've been hearing all day that short GRBs comes from binary neutron star mergers. And again, when 1708-17 happened, this 1.7 second delay and this gamma ray burst, which was short. So the shortness of the gamma ray burst just refers to essentially how long this gamma ray emission lasts for. And so short is essentially saying that it lasts for 2 seconds at most. And so when 1708-17 happened, we were all really happy because short GRBs, binary neutron star mergers, we've been saying that for a long time. Whereas long GRBs, we'd again been saying for a very long time that they're linked to core collapse supernovae. But then again, the universe likes to sort of kick us every now and then. And so when it did, the universe threw another spanner, which is this amazing couple of discoveries. And so this is a plot showing basically the gamma ray light curve again. So that 1708-17 plot, but for a different object. And this GRB is known as 211211A. And instantly, the thing I want to draw attention on is that it lasted for about 80 seconds. And really, I mean, it was producing quite a lot of emission at 30 seconds. So it's an order of magnitude longer than 1708-17 was. But immediately, we did some detailed follow-up. And so the optical emission is actually really consistent with a kilonova. This is quite puzzling. A long GRB should not be accompanied by a kilonova. It should be accompanied by a supernova. What's going on? And so that was all good. But then in 2023, we got another observation which had the same thing. This was now an even longer GRB. This one lasted for about 100 seconds. And again, if you look at this light curve, there's the afterglow emission. And on top of that afterglow emission, there's a kilonova, which is very, very similar to 1708-17. This is getting really puzzling. So these observations are of a system that is much, much longer in terms of what its engine is doing, but the kilonova looks remarkably similar to 1708-17. And if there was only these sort of observations, you could argue that transient light curves are really degenerate. Maybe it's just not a kilonova. In fact, for 211211A, there was few papers that basically said, no, it's not a kilonova at all. It's just an infrared echo. So it's just dust, and dust is making a little echo. But for the second object, 230307, we got an amazing JWST spectrum. And so this spectrum is, I think it speaks for itself for a lot of people here, but it's an absolutely incredible observation. And this is really only possible thanks to JWST. So what I'm showing on this plot is, again, the flux and the observed wavelength, but then a spectrum at a few different epochs. And the one I want to first draw attention to is basically the 2017 spectrum at 10 days. And so you can see this orange line, which only goes up to 2.5 micron or so, but it's got this little bump at 2-point-something micron, 2.1 micron. Very nice. This black curve is the spectrum for this new GRB, but at 29 days, so much longer, later epoch. And then again, we took another spectrum at 61 days, and we found this. The cool thing about JWST is JWST can take spectrums like this, and even better, better than this, out to about 400 megaparsec. And it can take photometry out to a redshift of 1.5. Amazing instrument. We just have to get really tight localization so we can actually spend time observing them. But the interesting thing about this is, I really want to stress, is that this was a long GRB. This was a system that lasted about 100 seconds, 2 orders of magnitude more than 1708-17's GRB seemed to do. But for some reason, it makes the exact same feature. Where is it gone? It makes the exact same feature that we saw for 1708-17. What does this feature actually correspond to? I think if you listen to Stephan, there's healthy skepticism to say whether what it is actually what we said it was. In the paper, we said it was tellurium, and that's basically entirely based on storytelling in a sense. We expect tellurium to be there. It's an abundant R-process material, but there could be 100 different lines that could correspond to that emission feature. So really what element it is, we don't know. But it's the same feature at a much later epoch with a completely different engine and progenitor. What is it? And I'm not going to give you an answer, so hopefully, there's some questions to be asked at the discussion time. And I really want to stress that, we're starting to observe neutron star binaries in ever more detail. And not only in gravitational waves, and I'm going to use that cliche that they are a new window to the universe, but we're getting a lot of these observations of these other objects in other ways. And I think it's worth looking at what the combination of these observations are telling us. And with that, thank you so much. And I'll...
Nikhil, questions? All right, Monica.
Thanks for the nice talk. So, a few slides ago, where you were showing like 211, 211, and other, this slide. Yeah. So, from a modeling perspective, we know that there are diversity of kilonova that can exist, and also from nucleosynthesis perspective, you would expect so from like binary mass ratio and everything. So, I am a bit curious about this, that this object and the other one also looks very similar to 17/17. So what's happening? So is this like all the light curves we are expecting to be similar? Like, what's the current take of it?
So it's a really good question, and I think at the moment I would say that the answer is not clear. One of the things that for 2112A, 11A, and this is I think a much more of a modeling question that I really want to stress, is that what we did for 2112, 11A is we fitted the afterglow first, subtracted that, and then fit this kilonova itself. This is problematic for many reasons because A, we don't know how to model the afterglow really well. It's one of the better transients we can model, but it's still really uncertain. For 230307, we did a much better job, but there still we have some problems. And actually, I mean, since you are interested, I'll tell you the specifics. We are looking into 230307 again in more detail. And what we find is that there's a whole bunch of different kilonova models that can fit it really well. There's a big uncertainty in whether the afterglow is dominating the early time or the kilonova is dominating the early time emission. And that's the big uncertainty. And so if you believe that the afterglow is dominating the early time observations, then basically every single sort of kilonova model you can put out will fit the observations, even a magnetite-driven kilonova. Whereas if you believe the early time observations are coming from the kilonova and not the afterglow, then there's essentially only a series of models that can actually work. And so that is, I think, the question that you simulation people really need to tackle immediately, I think.
Thanks. We can discuss more later.
Yep.
Any other questions for Nikhil? All right, doesn't look that way, so let's thank you again. And let's see, so last out is Evan O'Connor, and this morning the question was asked, what about gravitational waves from supernovae? So I guess, you know, finally we get to learn about that.
Yeah, so you get a 15-minute answer. Okay, so I'm Evan O'Connor from Stockholm University, and I simulate core collapse supernovae. This is part of my research. So this is one of our simulations here that we do. It's rapidly rotating, and this makes a very characteristic gravitational wave signal, and that's what's shown there in white. And this will come up throughout the talk, this characteristic gravitational wave strain here. Thank you for the introduction, Ariel, and thank you for the invitation to come here and talk about gravitational waves from supernova. So I'll have a quick introduction to supernova, but then mostly just talk about the gravitational waves from those. So this is this simulation is about half a second. This is when the massive star collapses. This is when the gravitational waves are emitted from a core collapse supernova, and it's when, you know, essentially the decision is made whether a neutron star or a black hole is formed. Okay, so what is a core collapse supernova? It's a massive star that collapses. This is a recent core collapse supernova 2024 GGI, very close by, 7 megaparsecs. I think this is what maybe Patrick was referring to this morning. Only a month and a half ago, fairly close, but still 1,000 times further away than the galactic center. So it's important to keep that in mind. And 20 years ago, the same galaxy was imaged. And at the location of the supernova is the proposed progenitor of this supernova 2024 GGI. And it's a star that's consistent with something like a 12 or 13 solar mass star that's 1,000 times the radius of the sun. And it's a red supergiant. So that's what you're seeing in the image there. Not 20 years ago, but rather 2 months ago, probably, there was an iron core sitting in the center of this star at 1,000th of a solar radius. So 1,000,000th of the radius of the red supergiant was the iron core that was about a solar mass and a half, and that collapsed in a fraction of a second to form a protoneutron star. And then over the course of another second, like in the simulation you saw there, it's decided whether a neutron star or a black hole forms in that event. And so this is why I like to think of core collapse supernovae as the gateway to the compact universe. So it's where the compact objects are formed. Understanding how this happens, so how the iron core in a massive star collapses and an explosion is formed, has been a very difficult problem in astrophysics, and it's what we spent a lot of time on. What is clear is when the core collapses, you form your supernova shock, but it has to essentially from the beginning start undoing stellar evolution. It's breaking up iron into neutrons and protons. That takes a lot of energy, and so the supernova shock stalls. And you really need all these ingredients here that I list here in good physical detail in order to obtain explosions in these stars. The mechanism that we think is responsible for explosions in these stars is the turbulence-aided neutrino mechanism. So this mechanism relies on neutrinos coming from the blue region here, the cooling region, streaming out into the red region where they are preferentially absorbed rather than emitted. And so this increases the heat, increases the temperature of the material in this region and heats the material. It also drives convection and turbulence in this region, and this increases also the effective pressure of the material, and this is what we think causes the explosion in these massive stars, re-energizes that shock and gives rise to the explosion. This has been quite successful in the past 10 or so years. 3D simulations can explode when we simulate and include all of the physics here. This is just one example, a recent example that shows many explosions of many different progenitor stars. Okay, this is a couple more movies looking at two aspects that are very important for gravitational waves in core collapse supernova. So the difference between these two movies that you'll see is one has perturbations in the silicon and oxygen shells surrounding the iron core, and they seed turbulence, and you'll see that in the movie. The one on the right will have much stronger turbulence happening in the post-collapse phase. So the outer layer of this is the supernova shock wave, so that's propagating out. You see the neutrino-driven convection and turbulence happening. And right around 200 milliseconds, which is coming up, you'll see this difference between these two simulations. So the seeds of turbulence in the outer layers, when they fall in, they excite the strong turbulence in the one on the right. The one on the left doesn't have such strong turbulence, but it does have other coherent mass motions that are happening in the region between the protoneutron star, which is in the center here, and then the supernova shock on the outside. So these two aspects, turbulence that's happening in the core collapse supernova evolution, and these coherent mass motions are two important ingredients for gravitational waves. And we'll talk about some more for the rest of the talk. Unfortunately, unlike mergers, supernovae are a relatively poor source of gravitational wave energy. So most of the, unlike we heard this morning in the case of neutron stars, most of the mass in a supernova is not moving, and the mass that is moving is not really moving coherently, and it's not really moving very fast. And so these aspects together give you this efficiency parameter here, this epsilon, that's much less than 1. Okay? We would like all the mass to be moving very coherently, but this is not typically what happens in a supernova. So the best strain we can maybe imagine is something like a few times 10 to the minus 20, but only in a few cases are we going to get somewhere near there. And this is for a supernova at 10 kiloparsecs. That being said, gravitational waves are a unique messenger of what is happening in the core of these massive stars. So they relay information about the dynamics of what's happening, the mass motions, this turbulence that we were seeing before. This is complementary to neutrinos, which are also kind of a direct probe of what's happening in the core. But neutrinos tell us more about the thermodynamics of what's happening, and the gravitational wave tells us about the dynamics. So they're very complementary, very important to understand both of them. Because I mentioned that most of the mass is not coherent, most of the mass motions are happening from turbulence and stochasticity. And so this is why the gravitational waves are relatively weak, and they're not really, except in some cases, templatable. So we can't use a template. We don't know exactly what we're going to see. Quickly, I'll go over different sources of gravitational wave radiation in supernova, and then I'll go into them in more detail. So one is if the star is rotating. One is this oscillations of the material in the protoneutron star that comes from predominantly related to the turbulence. Another is these coherent mass motions in the gain region. And then lastly, asymmetric matter motion. So whether it's from asymmetric neutrino emission or asymmetric mass ejection can give rise to gravitational waves. So we'll go through these coming up. This figure was by Michael Picos. Okay, so rapid rotation. If you have a star like that one we saw on the first slide that's rapidly rotating, you form this very distinct gravitational wave signature, which you see here for many different equations of state, essentially all overlapping each other. And this is for a particular progenitor and particular rotation rate, but for fixed angular momentum, the signal will look the same as well. And as you vary the angular momentum, you just essentially change this delta H plus term. So you scale it up, but the overall structure is very similar. And this, because you have this rapidly rotating core as it's collapsing, the asymmetry factor, this epsilon that I was mentioning, is actually, is 10%. So you get strains of order 10 to the minus 20 here for a very short period of time. So the time scale down here is in milliseconds. On a much longer time scale now, so hundreds of milliseconds, as this mass is accreting and this turbulence is happening and the explosion is being initiated, the gravitational waves we see mostly come from turbulent motions that I mentioned. So here the strains are much smaller. There may be a few times 10 to the minus 22. And this is just several, 4 different 3-dimensional simulations that show typical strains in this period. If you take a spectrum of these and decompose the strain into a spectrogram, then you see essentially the characteristic core collapse supernova gravitational wave signal. So this starts around bounce, and slowly as time goes on, as matter accretes onto the protoneutron star and its mass goes up, then you have this dynamical frequency of the central object increasing, and you get this ramp up of gravitational wave frequency. And what sets this frequency is essentially the dynamical frequency of the protoneutron star. It goes like the mass over the radius squared of the protoneutron star. So as it cools and shrinks, the frequency goes up, and as it accretes mass, the frequency goes up. You also see here some emission at lower frequencies due to this coherent motion of material in the gain region, so that standing accretion shock instantly. The 2 colors in the plot there, the blue and the red, are these 2 different simulations that we were watching. So the blue one was the one on the left without the seeds of turbulence, and the red one is the one with these seeds of turbulence in the conductive shells outside the iron core. And when they excite that turbulence and the turbulence accretes onto the protoneutron star, it hits it, it rings that protoneutron star, and then the protoneutron star emits gravitational waves. And so that's what you're seeing, the difference between the blue and the red. This is the spectrogram for the blue one, and this is the spectrogram for the red one. So you see this burst of gravitational waves right when you have this much more turbulent motion happening in the gain region. Okay, so many people have studied this. Many people have looked at the impact of various physics on this diagram, and I can't get into any details of that, I'm sorry, but there's lots of interesting phenomenology there. Okay, another type of gravitational wave radiation that we can get is due to phase transitions in the protoneutron star. So if you have an equation of state that has, say, a first order phase transition from a hadronic neutron star to a quark star, then when this phase transition is triggered, it happens very quickly, and you have this large abrupt change in the structure of the protoneutron star. And if you have any asymmetries in that star as it's collapsing, then you'll get gravitational waves from that. So this is a movie of that process. So we see the shock go out, we see the turbulence that you saw in the other movies we've been looking at. And this will zoom in now, and we'll see the central object collapse and a new shock form. This is the phase transition shock. That's actually, in this model, fairly strong. It blows up the star. But that burst of gravitational waves when that protoneutron star was collapsing is quite strong. So this is now the strain of that. It's very similar to the rotating core collapse situation. So we have strains of order 10 to the minus 20 from this burst of radiation as the protoneutron star, as the protocompact star collapses, because now we have quarks, not just neutrons and protons. Okay, so then another mechanism, kind of unrelated to the turbulence, is from, or maybe not so unrelated, but is from this asymmetric emission of neutrinos or asymmetric ejection of mass as the star is exploding. And this gives rise to a low frequency, but very high value of the strain, in this case something of order 10 to the minus 21 in these pictures here, but can be even bigger in other models, especially if you have large asymmetries in the ejection. So we have a local expert on gravitational wave memory here. He's in the audience, and this is work from him. Okay, but what about the detectability? This is so not what I work on. I just make the signals. Other people try and detect them. But this plot shows what they have done is they have taken supernova during the O3 era, taken the noise from the O3 around when these supernova occurred. We don't know exactly when the core collapse was, because this particular one, for example, was at 15 megaparsecs, I think. So we don't have any neutrinos or anything like that. And they then take the noise and eject these signals from all these different models. Some of these models you've seen on here, they're all three-dimensional models. Some are rotating, some are phase transitions, lots of different examples. And they inject it in the noise and see how far they can detect these signals from. And they essentially get, for the generic neutrino-driven turbulence cases, a few kiloparsecs at a 50% detection efficiency. And then for rotating ones, maybe like the cyan one here, is a rotating core collapse, very similar to the movie we had seen, maybe out to 10 kiloparsecs for O3 the detector sensitivities. Okay, next generation maybe can push this out to beyond the galaxy, but not to the next galaxy. Right? And this is work showing for advanced LIGO the distances for many different three-dimensional models, and then also for the Einstein telescope, Cosmic Explorer, going out to, say, hundreds of kiloparsecs, but not out to the megaparsec scale where the next galaxies are. This is kind of detecting a supernova. Of course, extracting parameters then is even more difficult, but this is what the community is working on. We really want to leverage a gravitational wave detection as much as we can to learn about what's happening in a core collapse. Okay, so in summary, here it is, and I can take any questions.
Questions, Rowan? Huh. There you go.
So you said that the gravitational wave signatures are very stochastic and not very templatable in that sense. Would it be possible to at least make some halfway step towards some templates, in the sense that in many of the supernova spectra I've seen, there's some arching signature and then some other features where the existence of the features are at least somewhat common.
Yeah, so excess power searches, but at particular frequencies that you prescribe, you say, this is what I expect the frequency ramp up to look like, and that's better than just looking at it blind, right? Yeah. That frequency ramp up, of course, depends on some of the underlying physics, right? And it's not necessarily always sharp. Sometimes it can be broad. It can go up fast, can go up slow. So there's still a lot of uncertainty there in what it looks like. Yes, but.
So do I get it right that most of your stars are single stars, but most massive stars are in binaries? Does that help you?
It helped me in what way? In blowing them up?
In getting more gravitational waves.
I don't think so. So I mean, my personal take on binary evolution and how that affects quark collapse supernova is that obviously it affects the progenitor and it affects what the star looks like at the end of its life, but it's not necessarily going to affect the 1 second where the gravitational waves are emitted. And so that signal is probably safe from effects of binary interaction, but of course, where the what is the typical iron core mass of a star, that can of course depend on these the binary evolution and population synthesis. So this is important, but these cores that are collapsing are not really going to be affected by that directly.
All right, I don't see any more. Oh, I see a question.
Yeah, so I guess a core collapse supernova within the galaxy is probably the only source where we might actually see both photons and neutrinos and gravitational waves, right?
Yeah.
So even if we wouldn't immediately find a signal, we would hopefully have a pretty good idea of exactly when and where
That's right.
the supernova occurred. How much does that help in these searches?
In for the gravitational
Yeah.
waves, for example. Yeah. Sorry, I forgot a word here. Right. This is ultimate multi-messenger. In terms, I mean, the number I have in my, of course, it's important. If you know from neutrinos exactly when core collapse happened, then you don't have hours to search over, right? You have a time to search over. You have seconds essentially to search over. So that is important in terms of increasing your signal to noise, of determining whether the gravitational waves are there. You're going to have to ask a gravitational wave detector person. In my head, I have a number of a factor of 2. So that is what I have in my head, but I could be wrong. So if someone else knows that, they can.
All right, let's thank Evan. Before I give the floor to Bengt, I think I could ask all the speakers of today to come forward. We have, again, Veronica and Peter have prepared some gifts for you guys. So please come forward so we can you can receive the merch from the Academy. Okay. I'll be the deliverer. So again, thank you all very much for being here today. And we want you guys to be hydrated. So.
Thank you.
Thanks a lot. Yeah, there you go. Thank you.
The bar is really high for the next talk I get.
Thank you very much.
Thank you.
There you are.
Thank you.
Wonderful.
Thank you
so
so
thank you all.
Cool. Can we go now? No.
Great. Thank you very much again. Yeah. I know, Bengt, if I please can ask you to guide us through what we just witnessed. Okay? Ska det bra? Va? Klassar bara. Ja, men det med KVAs det fina.
What an interesting and promising meeting we have had. And what a promising and interesting field. It may be a place, however, while enjoying these achievements and future possibilities, to remember the early development, the pre-LIGO phase of the area. I stayed at the University of Maryland
in the 1970s for some periods and met with Weber several times. He constructed, as you know, his sets of resonant mass antennas, massive aluminium cylinders, huge things, placed in different places, and measured the vibrations of them with some sensors and looked for coincidences between the different cylinders to trace the gravitational waves. There were tens of different experiments of this sort. First, the Weber's bars, as they were called, but later on also cryogenic ones in different places. No success. There were reported successes, and Weber, he developed from great enthusiasm to triumph, to depression, and sometimes even with scorn from the surroundings. As you may remember, Isaac Newton is said to have said that he was standing on the shoulders of giants. And I guess that's true for all of us. But we also stand on the tombs of failures. And I think it's due to really pay some credit to all these people who have tried and tried, seen possibilities, but explored different ways, more or less difficult, more or less hopeless, but still made the foundation of what we are doing. They did not succeed. They were never celebrated. Let's think of them anyhow and bring them into the history of our success. We have learned a lot from the talks today. Actually, I'm quite overwhelmed by the developments and all these new facilities and possibilities that are ahead of us. I did discuss this meeting with one of my grandchildren the other day as a preparation for me. Assume, I said to her, that you had spent all your youth in your bedroom with the curtains pulled down, and that suddenly somebody came in and the curtains were lifted up and you could see what was outside. How would you experience that? And she said, I wonder if I would understand anything of the world outside. Are we in a better situation? At least we are, should be duly so, totally overwhelmed. We look, that is, forward, maybe with some anxiety, to a future with an inventory of all compact object mergers through the history of the universe, at least out to the cosmic horizon. The ones that occur at the right times in the history back. No black hole is left behind, as Sheila Rowan said. Some needs are then obvious. The need for handling all this information in a smart way. The need not to miss the totally unexpected. The need to take account on not only what we see and fit by simulations, but also to understand what we see and fit.
and understand what really happens in reality out there. We also need to explore the new gravitational wave data for a number of important applications of more or less classical problems in astronomy and physics, like equational state of dense matter, the production of R-type process elements, of core collapse supernovae, of energetic jets and the mechanisms behind, the nature of gamma ray bursts, and of course the Hubble tension, the formation and evolution of massive supermassive black holes, and of course nature of gravitation at very dense in very dense environments. We shall of course need AI and good students, many students, and engineers, very bright engineers compared to most of us, postdocs, and other bright persons too, and patience, international collaboration, sometimes in very large teams that have to be formed. No doubt, all goodwill in a peaceful world. Hopefully, these common efforts, however, will demonstrate to all humanity the possibilities of us, or humanity as a whole, to solve important and difficult problems in constructive and peaceful collaboration. Maybe that's the main objective of what we do, just to show that humans can do this if they organize themselves in a constructive and meaningful way. On behalf of the organizers and the Academy, I wish to thank all speakers who have come here and contributed so greatly. And we also have to thank Peter and Veronica for their technical and organizational support. Did you get any bottles? You did? Oh, you should have, but we have to ask the Academy board to supply them. I wish you all a good final of this meeting. There'll be some food, and after that, Kip Thorne will address us. And then we have to go home and work. As this meeting has shown, there's very much work to do. Thank you.